the YouTube stream. I do that way too much. Okay. I think I'm good to go to get started. Oh, that was me and Fembox saying hi to each other in the Excalibur. Oh, I need to go on open mic. There we go. Okay. I'm in Discord Fembox, so whenever you're ready. Oh, good, my overlay is still working too.
Hey.
Hello, hello. How's it going?
Hey, Don. How you doing? Doing good here.
Good too. Are you drinking tea
Now,
or coffee or anything to fuel up?
Oh, I had my obligatory 2/3 of a pot of coffee this morning. Yeah, so I'm
Okay.
good to go.
Nice. Okay, so
let's see. Let me see if I can work out Discord. So I got you on voice on Discord, but now I got to work out how to get the Excalibur up at the same time.
oh, okay.
Okay. I think this. Oh wait, it says leaving Discord. Well, maybe it'll still work.
Oh, worst case, you just rejoin.
Yeah. You still there?
Yep, I can hear you.
Okay, cool. Wow. Okay, everything's going.
Oh, good. Okay.
100% iPad.
Hell yeah. APR Gaming.
I'm getting better with this thing. Last time we did a reading group, I was on the iPad for the Excalibur, but I was on the PC laptop for the Discord voice.
Oh, yeah. I mean, I guess doing it all through the iPad is probably more convenient. Femvox plus Don factorial, is that called Femdon? I guess we could call that. That might be a different kind of stream though. Okay, so
Well, I looked into calculus of variations yesterday, but I didn't really get very far with it.
okay, and yeah, that's fine because I was just like going off both like the notes that I took from the lectures and like the class textbook that's written by the professor of the class, and it's kind of a lot to like get through those. So I felt bad I didn't have anything to like refer you to those that good, but yeah. Hopefully,
Well,
nothing to do
I
with too
only
bad.
had the whole internet at my disposal, so I was hard pressed to find anything.
Yeah. All right. I guess you ready to get into it?
Sure.
Okay. So for calculus of variations, like the basic problem that it solves. Let me just make sure I get this right for my notes. We're gonna define a quantity j of y. I'm on the thinnest pen possible. It still feels kind of thick though. Oh well. J of y, and j is a functional, so just using the square brackets to say it's not quite the same as a regular function.
Oh.
But it takes some function y and it spits out a real number.
Mm.
And it's defined generally as the integral from a to b of some function of x, y, and y prime. So when we were doing like general relativity stuff, this function could represent like the arc length on whatever space-time metric you're working with.
Mm.
Or if you just want regular Euclidean space, you could do 1 plus y prime squared for an arc length integral. And so the task is to find the minimum y. So, or the y that minimizes j. And for now, we're like the space of y's that you're searching in is really important. For this first part, we're going to talk about functions that are at least differentiable once, so C1. It turns out you can actually make that less restrictive. But C1 is a little bit easier to work in.
Does the letter J stand for anything in particular?
I don't think so.
Okay.
The kind of general word for it is the performance index.
Oh.
And so the context that you and I were learning about it in, we just called it distance, but it could also be like profits for a company. It could be like the numbers of a certain type of cell that a disease produces, or the amount of glucose a doctor gives to a patient. There's a lot of different things that it could be.
Yeah.
And F is kind of generally called a Lagrangian, same as like with Lagrangian mechanics. I think it was like K minus V or something. For like the general relativity context that we talked about it in.
Yeah, don't rely on me having
Okay.
remembered much of that. But yeah.
No
Yeah.
worries. Okay, and so there are two other restrictions on the function. So we're trying to find the minimum j, but we also want the function y to meet certain like boundary values. So y of small a equals big A, and y of small b equals big B. And
the two A's and the two B's are numbers?
Yeah, just real numbers.
Real numbers, yeah.
These are the same things like for a boundary value problem for differential equations. And so any function y that meets these two conditions here and is in the space that we're searching in, we call admissible. As in, we're just allowed to plug it in to the Lagrangian f. Okay. So that's like the problem that we want to solve. And the thing that basically Euler first found that is like the genius thing he did to like figure out how to solve this problem is he figured out a way to convert it to like a regular like first semester calculus problem. I mean, a little more advanced, but basically that. And so the cool thing about what we'll be talking about today is it's actually going to be really parallel to first semester calculus stuff. So
well, I hope so, because I'm good at that stuff.
Okay. The first thing we're going to do is we're going to just suppose that like whatever y that minimizes j exists, and we're going to call it capital Y. And so in math speak, I'll say argmin y in C1 j of y. We're going to define it as capital Y. So just assuming it exists, I don't know about questions of like existence and calculus of variations. We never really covered that, but for all this, we're just going to assume that it exists.
Okay.
And so we're going to build comparison functions. So if y is the optimal comparison function, or sorry, capital Y is the optimal comparison function, we can think of other functions kind of close to y, and we're going to call them just like a generic small y is equal to our big Y. Sorry, these are like, I should emphasize that these are like functions of x, including up here in the Lagrangian.
Yeah.
So yeah, small y of x equal to big Y of x plus some variation. So we're going to create a parameter epsilon that's small, and some sort of test function h. Test function is not the right word for that, but just it's kind of any function you want, but we're going to require that it's 0 at the endpoints for 1. And we need this because it ensures that this small y that we're building is still admissible. Like it still needs to meet the end conditions of the original problem.
Okay.
And so since capital Y by definition must meet those end conditions, we just want h to be 0 at either end.
At the end points, yeah.
Mm-hmm. And I think this isn't strictly necessary, but to make things simpler, we're going to also let h be differentiable once, at least once. Okay. And so now what we do is we're going to consider j of like our small y, which is this capital Y plus epsilon h. So I'm going to drop the of x's just for the sake of not writing too much. A to b. F of x, capital Y plus epsilon h. Oh, I should say, we can take the derivative of each side of the equation to find out what small y prime is. This one is pretty straightforward, just capital Y prime plus epsilon h prime. So this is y prime plus epsilon h prime dx.
Okay.
And yeah, there's a little more that I can say about this construction, but I want to get to the next step first. Okay, so in Calc 1, when you... Oh, I want to add one more thing. When we consider j of y plus big Y plus epsilon h, we can kind of start to think of j as a regular function of epsilon now. Because epsilon is just a real number, and we're kind of holding y and h as constants for the sake of this next calculation. So then in like first semester calc, what do you usually do to find the extreme points of a function?
Well, you differentiate it.
Instead of equal to 0.
Differentiate it instead of 0, yeah.
Exactly, yeah. So we're going to take the derivative of this thing with respect to epsilon, because that's what we're kind of... That's the thing that's kind of like varying us, that gets us away from our optimal function y that we want to find. And so as it turns out, the condition that we want to meet is the derivative of j with respect to epsilon. Okay, yeah. So the goal is we want to find an explicit form for like the capital Y, because we don't know what it actually is yet. And so since it's the function that optimizes the value of this integral, we're taking the derivative with respect to epsilon. We're going to then plug in epsilon equals 0, so we just get capital Y back out.
Mm-hmm.
And then we're going to set it equal to 0, because that's when extreme points happen. So this is the condition that we want to satisfy to find an extremal capital Y.
And what about this h? Is h fixed?
H, yeah, it's kind of...
H could... Yeah,
it could be anything.
Okay.
Yeah. And so we're not going to actually change it. Like it's important, but it's going to kind of go away pretty soon too.
Okay.
Okay, so first up, let's figure out the derivative of j with respect to epsilon. So assuming it's... or if you make the right assumptions, you can justify interchanging derivatives and integrals here with the Leibniz rule, I guess. Okay, and so this derivative here is a little tricky to take with the chain rule. Do you see what it should look like?
No.
It's okay because it's really kind of weird.
Is it like a are we? It's not really a partial derivative with respect to epsilon, is it?
No, there will be partial derivatives involved, but not for epsilon.
Hmm. It's a function of 3 variables, right?
Yes, this is still like an invisible small y, and that's still invisible small y prime. So you think of it as like
I don't know.
of
You're gonna
epsilon.
have to show. You're gonna have to show me. I don't know what comes next.
Yeah, that's okay because it's kind of hard to figure this out if you haven't seen it before. Um, math hard. It is hard, famished. Okay, so um, x doesn't have anything to do with epsilon, so we don't have to worry about that. The second argument, small y, it is a function of epsilon, so we do need to worry about that. So we're gonna get a partial derivative of f with respect to small y, x y plus epsilon h y prime plus epsilon h prime, and then chain rule.
H.
Yeah, exactly. But we also have to deal with the second argument that also depends
I see. I
on
see.
epsilon. So we'll add it to partial derivative with respect to y prime. Same inside. It's a little bit annoying to write all this out, but it's kind of important for the part after this. Epsilon h prime, and then times h prime now instead for chain rule.
Okay.
Nice. So that is step 1. Step 2 is to let epsilon be 0. That's a little more straightforward. A to b, f sub y, x, now it's just big y prime h, plus f sub y prime, x, y, y prime, h prime, dx. Okay, and so this is the thing that we're going to set equal to 0, and we want to squeeze like something we can actually work with out of this left-hand side here. I don't expect you to know the answer here, but do you have any ideas for how we could proceed here?
I do have an idea here because it reminds me of something I read yesterday. Do we have to integrate by parts now?
Yes, perfect.
Yeah, I don't see how to do it, but I know that's what they did at some point. Integrated by parts.
Oh, sorry, I just wanted to just finish. I'm glad that you logged in. I hope you give it another try at some point. But sorry, what Femlux?
I was just gonna say I think it's integration by parts, but I couldn't do it myself. You know.
Yeah,
I wouldn't
that's
even
fair.
know. Like, yeah.
So the goal that I'm working towards here is I want to like we don't know what to do with the h's, and I want to get rid of them. As it turns out, you can and want to integrate by parts, or like that you can just integrate by parts on this term or on this term. Only do it to one, but it's important to try doing it to both. For this first part, we're going to integrate by parts here.
Okay.
So actually, maybe I'll keep writing it in green. So I'm just going to set up integration by parts the way that I know how. I want to take the derivative of, because I want to integrate h prime so it becomes just h.
Oh,
so,
I see.
And then du will be d by dx f sub y prime dx, and then v will be just h. Yeah.
Oh, and we know h is 0 at the endpoints.
Yes.
Yeah,
exactly.
That's gonna help us.
So for u times v, it'll be f sub y prime times h, evaluated at the end. I'll say x equals a to b. plus integral. The first term got left alone, so I'll include that here. I'm going to stop writing the argument of f minus VDU.
Gotcha. I see. I see what you did. So you brought this one back here too.
Mm-hmm.
Yep. Gotcha.
Okay. And so then, as you pointed out, this kind of boundary term here is just 0. Because of our requirement earlier, h of a equals h of b equals 0. And then from the inside of the integral, we can factor the h out. H dx. And we remember this entire thing is equal to 0.
Yeah.
Okay. So we're almost there. Just one more step.
Yeah.
We're going to apply what's called the fundamental lemma of calculus of variations.
Mm-hmm.
And the way that I think of it intuitively is that we know h is just some generic function that could be like anything, as long as it's 0 at the endpoints. So h kind of generally is not 0 is the point of this, but the entire thing is equal to 0. So we're going to set the other part equal to 0 and find what happens.
Yeah.
So fundamental lemma of COV, sure. And actually that's not an equal sign. Maybe I'll make it an arrow. Minus d by dx f sub y prime is equal to 0. And it's a little more commonly written with the two terms equal to each other. And our boundary conditions still carry over. So this thing right here is, I mean, there isn't really one agreed upon name, but we called it the Euler differential equation.
Okay.
Once
we learned it as Euler-Lagrange, didn't we?
I think so, yeah. And that's how the Wikipedia page called it too. In our class, we use Euler-Lagrange for a slightly different version of this that we'll cover too. Yeah, so like once you plug things in, like f is a function of x, big Y, and big Y prime. And so when you plug everything in, you'll just have an ODE for Y, for big Y. And whatever the result of that ODE is your extremal.
Okay.
I should say, oh yeah, I forgot to mention, when we integrated by parts, I believe that came along with the assumption that f sub y prime is differentiable in X. I didn't get myself enough room. And that is an important restriction. Not sure is there any way for alchemy to be scientifically possible? Not that I know of.
Okay, let me just remind myself of what the notation means too. The capital F subscript y means the partial derivative of the function f with respect to y.
Yes.
Yeah, okay. Yeah, I see it.
Okay.
Makes sense.
So yeah, like I like this because like the derivation of it, there's a little bit of awkwardness in there, but it's not that bad.
Right.
And a cool thing that you can do too is if you start with a differential equation, that's a boundary value problem, you could reverse this process we just did and find an equivalent calculus of variations problem.
Wow.
And so that's like how they it and that's why these like the two fields are kind of so connected, and you can let things be multivariable, and you find the connection between calculus of variations and PDEs. Yes, like on the final test, we're just given a multivariable like functional, and it actually happened to pop out as the wave equation, which was kind of cool.
Nice.
Okay, so now like that's like the big thing. Now comes a bunch of like technical stuff because this what we the process that we just went through actually put a lot of restrictions on what types of extremals we could possibly find, like what we'll get for capital Y. So one of the restrictions was when we integrated by parts, we restricted ourselves to only smooth extremals. So capital Y will never have like a kink or a corner or a cusp, well, whatever you want to call it.
Yeah.
It turns out extremals actually could have that. And they're like they do a better job at minimizing J than the smooth ones do. Or at least they can.
Oh.
Another restriction is that whatever extremal we find, it's inherently a local one, for the same reason that in Calc 1, when you take a first derivative instead of equal to 0, you're only ever finding local minima or maxima.
Yeah. Okay. Yep.
And then the last restriction that we implicitly made is coming back up to where I first introduced the function h. It turns out this second equation puts a restriction on y prime as well that isn't really necessary. You could rewrite it as small y prime minus big Y prime absolute value is equal to absolute value epsilon, absolute value h prime. But h prime is this, it's like a compact interval, and h prime is bounded. So we can just bound it above by the maximum of h and just say the whole thing is less than some constant epsilon naught. That's small. So by using this construction, we've put a restriction on y prime 2 that we wouldn't necessarily want.
Where did that come into our following calculations though? So you're saying if we do it differently, we can come up with a different because the only one I've ever seen is this Euler-Lagrange thing, but I know you were telling me there's other equations, right, that come out of all this theory?
Yes.
Okay.
And so yeah, for the one I just went out with like the derivative of y, I'm not sure how you get around that. There is a condition to check whether it's a problem or not, but if it is a problem, I'm not quite sure how you deal with it, to be honest, or if you can. Lucas, that's not right, but that's a fun way to remember it. Okay, so because of all these different restrictions, we would say that whatever y we get out of this process, whatever capital Y we get, is a smooth, weak, local extremal.
Oh, I did see that word weak somewhere when I was reading.
Yeah.
And they said weak ones are easier to find than strong ones.
They are. So the smooth came out because of integration by parts. Weak because of the restriction on y prime.
Oh.
And local just because of the nature of optimization.
So if we wanted to find, okay, so I'm thinking of local versus global, right?
Mm-hmm.
So if we wanted to get rid of this problem of locality, how would we do that?
So
I'm probably getting ahead of us here.
no, it's a good question because like I was gonna talk about that anyway. I think if there were multiple local extremals, you could actually just go back and calculate what the j of y is for each of those and compare them all. I think this
Oh,
process should get you all the extremals of this type. Because the ODE you get doesn't necessarily have a unique solution. Like you could have like y prime squared and things.
mm.
So yeah, I think that's how like the only way you could kind of generally deal with it. And so I was gonna say it anyway. If you get lucky enough, you can check for concavity. So if f is, hey collar cone, it's going well. Thank you. Hope you're doing well. What is bigger than infinity? Nothing. What is nothing? 0. So 0 is greater than infinity. I like it. If f is concave and y prime, any extremal is a global minimum. So that's like the trick. If you get lucky, you can just automatically have this for whatever extremal you find. And concave and y prime, it's just the exact same process as concavity for a multivariable function. So you need to check the Hessian matrix and find if it's positive.
Would we think of that as concave up? Is that how we
Yeah.
think of it?
Oh yes. Sorry.
It would
yeah,
be convex if it was the other way.
exactly. Yeah.
Okay.
And I forgot all that. In the class we're using concave and convex, but yeah, concave
Yeah.
up is the way that I originally learned it too.
And when you say it's got, sorry, I might have missed something. When you say f is concave in y and y prime, does that mean it's derivatives with respect to, like, the second derivatives with respect to those things?
Yeah, like you could pretend that like y and y prime is just like an x1, x2, or whatever independent variables you want,
Yeah.
and just do your regular multivariable calculus procedure. So like you end up with like a Hessian matrix that looks like f sub y, f sub y prime, since partials are interchangeable, y prime, and you'll check if that thing is positive semi-definite.
Oh boy.
So we're not gonna actually like, we don't actually have to like go through that process, but it, like for a 2x2, it's really not so bad.
I mean, I've seen this stuff before, but my multivariable calculus is a little bit weak, unfortunately. But okay.
Well, that's why we need to do the dip grab curl stuff.
Yep.
More geometric convexity. Oh yeah, you can also define it with like graphs and lines. I don't know if that's easier to check though. All you do here is you would check that f sub y is greater than or equal to 0, and then you check that the entire determinant is greater than or equal to 0, and then you have concavity.
Okay.
Cool. So that addresses the local part of the extremal stuff. Let me just look through my notes and see what I want to get to next. I guess I've been saying extremal, and we should probably talk about like, is it a minimum or a maximum or what? So in Calc 1, how do you, once you found your extreme point, how do you classify it after that?
Well, we could check. We could do the dumb way and kind of check the values on each side of it,
Yeah.
right? If it's a function of one variable. But I mean, I like to do it with concavity,
Hmm.
like find a critical point and then check concavity. And if it's concave up, then it's a relative minimum, and or like I guess we could say if it's concave, it's a relative minimum, and if it's convex, it's a relative maximum.
Yeah, exactly. So, um, if we want to call it a minimum, we're going to look at oh, you know what? Actually, I think I did miss something slightly with this Legendre condition for where it comes from, but we can classify it using the Legendre condition. I want to say it starts by checking like d squared j d epsilon, or like the second derivative in epsilon. And if you follow that through, what you end up with is if you have f sub y prime greater than 0, you have a minimum. And so that's still like a second derivative that we're checking its sign. So it's really kind of similar. And actually, and I should say this is necessary but not sufficient.
Okay.
So just like the second derivative test in Calc 1, it does have those weird edge cases where it actually doesn't work.
Yeah.
The same is true here. So, if you want to be sufficient to have a weak local minimum, you want to satisfy, first off, the Euler DE. I should say smooth weak. You want to satisfy, oops, the Legendre condition. You do the same thing for like maximization too. We just tend to start off with minimization because it's pretty much the same process. The third condition is called Jacobi's test. And this one's a little technical and I don't understand it fully for myself, but your extremal y must have no conjugate points, which I'll explain. On the interval a b. So these are kind of conjugate points. It's kind of difficult to explain what they
Is
are.
that open closed on purpose?
Yes, it is.
Yeah. Okay.
The way that it was kind of explained to me is just with a counter example for why you need it, but it has something to do with symmetry points. It turns out if you where is this image? I'm missing the exact image that I was trying to find, but do you have the stream open, or are you able to see it?
Yeah,
Okay.
I'm following you. Yep.
Okay. So if you are solving the problem of shortest distance on a sphere,
yeah,
what you want is like the part of the great circle that is like the shorter part between 2 points.
Yep.
The issue is that just the first two conditions, the Euler differential equation and Legendre condition would say that also the other way around on the same great circle would also work.
Oh, I see. All right.
So it's
Which would give you instead of the global min, you'd get the global max out of it.
I think so, yeah.
I think so, right? Like if you had 2 points on a sphere and you had a great circle containing them, then I think the short arc of that great circle would be the minimum distance. I think the longer arc would be the maximum distance, wouldn't it? In a straight
at least
line
for a
on the
straight
circle.
line,
Yeah, it
yeah.
feels like it. Yeah.
Um so
Oh, I see what you're saying. Yeah, I'm assuming that we're restricting ourselves to a straight line there. Okay.
yeah, that's why I'm not like entirely like certain of what's happening here, but
Mm.
um the point is that the other part of that great circle would have like a point of symmetry with your starting point,
Yeah.
and you can check if that point of symmetry exists in your solution with Jacobi's test. Um, and so I'll just like show it on screen without actually writing it because it's a little bit annoying.
P's and Q's.
Yeah, I think it was just that thing that I had on the screen with P's and Q's, but there might be a represented better down here. Um, okay, I guess that was it. So it's just a differential equation for, we were using big H during the lecture. This small h is a little deceiving because it's not the same small h that we were talking about before, but
Okay.
The P's and Q's are defined in terms of your original functional f, and after you've already found your extremal, you would plug it into your functional f and get something just in terms of x. And then you take these things of just x and you plug them into this ODE here for h. And the moral of the story is if the solution to this ODE h has any zeros on that AB interval, then there is a conjugate point. And I guess I can write that on the Excalibur. So P of X, I'll use capital H. H prime of
Hey,
X.
Fizzbuzz.
Fizzbuzz, yes, that's what it's called. Jacobi's accessory equation. Minus Q of X. H of X equals 0. Ooh, it does have... The second boundary value for this OD is a little bit confusing, but we definitely have the boundary value H of A equals 0. H of B, I'm actually not sure about. I literally have it equal to a question mark written in my notes. The book is saying you let H of E be 0, but that doesn't make sense. And I think it might be for a slightly different context. So yeah, a conjugate point is one where H of C equals 0 for some C in the interval. So yeah, it's probably not worth going through and actually like deriving that, but if you have all three of these conditions, you do have a smooth, weak local minimum. That may not be what you want, but that's what you have. Hey, Sonal Kumar.
I mean, a smooth, weak local minimum sounds like a great start to me.
It is, yeah. And so I guess maybe we'll talk about how we want to make it stronger. So if we want a smooth, strong local minimum, Sonal Kumar, I'm sorry, but I don't know Olympiad math. We need satisfy conditions 1 through 3 again, but we now have a fourth condition. And how do I want to write this? We need the Weierstrass excess function, which we call E, x u v w, which is just generic. U, v, and w are just generic letters that we are going to plug in for in a second. We need this thing to be greater than or equal to 0 for all u v near y prime for all basically finite w. And so u, v, and w, you can think of them as functions, but you can also just treat them as kind of generic letters. And I'll write down what the Weierstrass excess function actually is. No, I don't stream daily.
Not yet, anyway.
Yeah. The Weierstrass excess function E of x, y, big Y prime, small y prime is equal to f of x, y prime. It's a little long. F of x, big Y prime minus y prime minus y prime. Oops. F sub y prime of x, big Y prime. Jeez. Yeah, so this one is a mouthful, but this function comes from considering in general j of small y minus j of big Y, where y is just any like other function you want, and big Y is your extremal. And you're trying to make sure that this is greater than or equal to 0, because just by nature, if big Y is truly your minimum, then this relationship should always be true.
Yeah.
And you kind of do some, you just like use a definition of J, and you are just clever with how you manipulate things, and you can eventually get the Weierstrass excess function out of it. And so the reason this removes the restriction on big Y prime that I talked about before when we use the H thing, or it doesn't remove it, but it checks it, I guess, because like U and V are kind of independent of each other, and the definition of like near Y and Y prime is a little bit vague, and I'm not sure exactly what they mean. That it's probably something similar to what we did with like the plus epsilon H thing, but we're using like two independent H's instead.
Oh.
Rather than H and H prime, I think. Over branch of math is probably differential equations. Okay.
Number theory, right? Number theory.
No. I mean, if you ask me which I prefer less between number theory and abstract algebra, that would be a challenge to choose one.
Oh no, really?
Yes.
Oh, I like both of those. I like both of those.
Yeah, I'm sorry. I just have a hard time with both of them.
How about between abstract algebra and real analysis?
Oh, I well, I definitely like abstract algebra less.
Okay.
Um, real analysis I have an appreciation for because it is pretty directly applicable to like numerical methods and just applied math in general. Like it gives you like the toolbox to do applied math stuff.
Oh, Flofi likes algebra too. Yeah, I like algebra. Yeah.
Yeah, I know. I feel bad saying because that's like a lot of mathematicians think of that as like the coolest thing in math, but I just can't get into it. Yes, Hono Kumar. I'm not much help in number theory. I'm sorry. Okay, so some of us do analysis and some of us do math.
Shots fired, as they say.
Yeah. Some of us do things that are useful and some of us don't. You know, it's okay. um, you don't. You do math. Okay, so I guess actually this is going a lot faster than I thought it would.
Well, maybe I'm not asking enough questions. I don't know. Or you could, I mean, you could do some examples if you want. I know you said you wanted to maybe stick to theory more for the most part.
Yeah, we could maybe get into an example. There's one more piece that we should talk about first, though, which is smooth versus
Yeah.
not smooth.
Okay.
So yeah, we've addressed weak, we've addressed local. So if we want to address smooth, it turns out that if I come back to the bottom, if you do this procedure for certain functionals with the Euler DE, you kind of just get some trivial extremal like y equals 0 that is true, but not all that helpful. And you can get non-trivial ones if you allow it to be piecewise smooth. So like an example that we were shown is like you start off on y equals 0 and then you suddenly turn into a hyperbola at some point. I forget which situation that exactly was for.
Yeah, maybe it's like the what about that old calculus question of, you want to get from a point on one side of the river to a point on the other side of the river, and you can run faster on the ground than you can swimming, and you
Oh,
want to find the quickest time to get from point A to point B, right? So
yeah, it's
I
probably
don't know if
something
that
like
would be
that.
it. I don't know if that would be something like this or not, but that's what it reminded me of when you said that.
Um,
Maybe it's not the same thing because your distance, like the path you follow, is not smooth as a path, right? But the time is still smooth as you move. So I don't know.
yeah, or like in that case, time would be like instead of using x, we'd be using t. But
Yeah,
like our function y, which is the actual path, would not be smooth.
right.
It'd be like a straight line and then diagonal line or something. Um,
Okay.
so I think that that is a good comparison. I can't actually find the
Yeah, something
example.
something I was reading yesterday said that x and y prime could actually all be functions of another parameter sometimes.
Oh yeah. Um, so
So in that case, I guess they could all be time dependent, for example.
yeah, and that's the thing that we did too, where you consider the integral a to b f of t x of t x, I guess we'll say dot for a time derivative now, y of t y dot t oops dt. And there's a little thing that I'm missing here because usually you would start with the original integral and then convert it to depend on t and you get like a little chain rule extra thing on the side. But yeah, you can definitely include time dependence in this. Okay. So the hey Leo. Time translation and variance and daring. Leo, if you start streaming on Twitch, it'll be a lot easier for me to catch you. I'll try to catch you on YouTube at some point, but I don't check my YouTube as much. I do want to catch you though. Okay, so the point in the derivation here where we kind of force ourselves, or we're restricted ourselves to smooth extremals is when we integrate it by parts. Right there.
Yeah.
And if we want to get around that, we can actually integrate by parts on the other term instead.
Wow.
And because we already assumed that h is differentiable anyway, so there's no issues with taking the derivative of h, and we will end up with an integral of f sub y, but that's okay. So it'll be a really similar process. I guess maybe I can even copy paste it. Okay. And then I'm going to say PWS as an acronym for piecewise smooth extremals. So yeah, I'll skip over the details here, but you do IBP on this. Ooh, no one got first. Hey, Skirtle. You do integration by parts on that term, and then instead of the fundamental lemma of calculus of variations, because that applies only for smooth things, you need a similar thing called the Dubois-Raymond, I think, lemma. Hey, TVSR. Let me just verify that in my notes. Yes. And what you end up with is what in class we called the Euler-Lagrange equation, but again, it's not really widely agreed upon to call that. Aerospace and satellite hacking. Ooh, that's cool. And the Euler-Lagrange equation is f sub y prime is equal to some constant c plus the integral from a to x f sub just y, and then a dummy variable, I guess I'll say, I don't know, s, y of s, y prime of s, ds. And so c is a constant. Okay, and so this is the equation that will get you piecewise smooth extremals, because we haven't made any extra restrictions on like the differentiability of f sub y prime. The issue here is that it's an integral differential equation.
Yeah.
So it's a lot harder to solve.
Yeah, I mean, I look at it, the first thing I want to do is differentiate with respect to x, which probably gets us right back where we were in the first place, I guess.
Exactly. Yeah.
Okay.
Oh yeah, I guess yeah, you would get exactly the Euler dE from before if you did that. So yeah, it's kind of annoying to work with this equation. If you do somehow know where corner points are, though, you could split it up into multiple different Euler dEs.
Oh,
Just like one for each like interval where it's smooth.
okay.
And so yeah, a part of the issue is that like if you're just handed a minimization problem with the integral sum functional, you don't know whether to expect piecewise smooth extremals or not. Because like you really you want to avoid the Euler-Lagrange equation at all costs. So um you can figure out if you should be concerned about piecewise smooth extremals using what are called the Erdmann corner conditions, or sometimes Erdmann-Weierstrass. So the first one is just f sub y prime is continuous even at corner points. And you don't know where they are, but so you just kind of check everywhere. Or you usually don't know where they are. And so in class we're doing a whole like process where you can consider f of xc, just some generic corner point. Sorry, f sub y prime. Now it's all like squished. X sub c, your potential extremal capital Y of x sub c, or your extremal that you're checking. I'm just looking at my notes to make sure I get this right. Yeah, and then y prime of x sub c as you approach from the left. Equal to f prime. So, oops, I need my c's. If it's just like checking from left and from the right at every point. X sub c plus. And we gave these like, we just called this q for brevity and that p. And if you can find places where p does not equal q, then you need to be concerned about piecewise smooth extremals. This doesn't always completely determine p and q though. So this one condition isn't always sufficient.
So P and Q are numbers, aren't they? They're not functions?
They're numbers, right? It's a number that we get by plugging into capital Y prime.
Yeah, so Y prime is a function, but we're plugging in this specific X corner point.
Mm-hmm.
I'm checking if the slope is checking if Fy prime. Oh boy.
Yeah, I lost points in the final because I still don't completely understand these, but I think if you find that like it's ever a point where p does not equal q, you can find out like what they would be, and if your y prime ever achieves that value, then you need to be concerned. I think it's something like that.
All right.
And so yeah, so there's a second condition for when the first one isn't sufficient. Let me find it. Yeah. Okay. Instead of, I guess I meant to define this a lot earlier, but just for the sake of brevity, I'm going to say that capital F hat is
No,
your.
I was going to ask you what the hats were in the book.
Yeah,
What
yeah.
the hats? Yeah.
I at first I was thinking that I should just not bother defining and just writing out entirely each time, but it's your capital F with your capital Y plugged in instead of just a generic
Oh,
small y.
okay.
Um, and so we often think of capital F hat. You don't have to, but you can think of it as just a function of x.
Okay. Yep.
Um, yeah, the second condition is f hat minus capital Y prime times f hat y prime. Same thing, is also continuous even at corner points. And this quantity looks super random, but it actually kind of comes up a lot. So much so that it's actually given a name, and that name is the Hamiltonian. This is like
Wow.
the negative of the Hamiltonian. But um, so yeah, if we do like follow up discussions, we can talk about like what you do with the Hamiltonian, but that's like what Hamiltonian mechanics is kind of about, as I understand it. And so instead of working just like the Lagrangians inside of that integral, you can like work with this too to optimize stuff.
Cool.
Okay. So yeah, I guess that's what I had prepared to cover. I guess I could have prepared more, but yeah, we can do an example or two. Let me see what Floppy is saying. Programming trying to get a master's in math in Panama is basically a master in differential equations. Gonna have to start grinding D's. Like it's more of an applied thing. I mean, if it's not what you want to learn though, like you should think about finding a different program though. A master's can be kind of difficult to get, so it's a lot easier if you enjoy what you're learning. I guess there's another thing I could show you here because like calculus variations, it has a lot of tricks that you can use if your Lagrangian is simple or has like certain qualities. I'll actually find where, so you can actually go through and derive this one. It's not too bad. Okay, so one trick is if your functional does not include x anywhere in it, it's just a function of y and y prime. We can think about the Euler dE, and there's actually a neat little simplification that we can do of it. Looking back at my notes for how this actually works again, you do some product rule shenanigans. It's taught by engineers. There's only one different program. It only teaches what would have been considered an undergraduate mathematics during my undergrad. You know, it's going to get me into a PhD. Yeah, Fluffy, that's difficult. It doesn't sound like you would enjoy that, but maybe you don't have a lot of options. Okay, you can multiply each side of that equation by y, capital Y prime. And these are technically f hats in the Euler dE.
Are they?
Yeah. If I come back up to where we derived it, I guess I did just write it wrong up here because I got lazy because I was dropping the argument of f, but it is f of capital Y prime.
Oh, right here.
Yeah. And so that same argument like carried all the way through. So
Oh,
I should have written
yeah.
hat.
Okay. When did the hat show up then? Was it
Um,
this line? Was it this line here?
the hat showed up.
Is it the hat then?
No, a hat would be
No.
it. That plus epsilon h messes that up. As soon as we took epsilon equal to 0, um, we uh we
Okay.
went from y plus epsilon h to just y. So when you have the just y, you can
Okay.
call it hat.
So this line.
Yeah.
Okay.
Actually, yeah. Let me just put hats back all the way through that work now that we know what f hat is. Hat, hat, hat. And yeah, Flippy, I think like not every school requires the GRE these days. That a lot of them dropped because of COVID, so it's worth looking into schools you might be interested in and seeing if they actually do require it or not. I guess when I was looking into applied math though, which is less likely also. For pure math, it might not. Okay. So going back to the bottom.
The GRE's fun. The GRE's fun anyway.
Depending on your definition of fun.
Come on, we all love it.
Uh, I had a difficult time with it. I did not do well.
I honestly took it for fun. One of my friends was, I already had a
Oh,
degree, and one of my friends was studying for he wanted to get into a PhD program and he had to take the GRE, and I said, I'll take it with you. So we took it at the
wow.
same time. I just studied for it and took it just to see how I could do.
How did you do, if you don't mind saying?
Uh, when was it? I was like a 76 percentile or something like that. I would have to look it up.
Okay.
I was somewhere in between 75 and yeah, somewhere up there.
Yeah, for the math GRE, I at least for when I took it, it was scored out of like 800 maximum, and I want to say I got like my best score is like a 680 or 650 maybe. Like it
That
wasn't
sounds good.
great.
Sounds good.
I don't think the percentile was very high. I remember it like it's not bad, especially because I crammed for it, but I think I could do a lot better today. And yet TVSR, the GRE is just like a standardized test for grad school. There's like a general GRE, but there's also like specific subject GREs, and the one for math is kind of difficult. um, what was I doing here?
You were doing a trick where where it doesn't depend on X anymore.
Yes. Okay, so
Oh, you said there was some product rule shenanigans. Yeah, I like this stuff.
yeah, this left side is what we want to rewrite as a product rule. So if we just did a bit of side work, like the thing that we want to end up with is d by dx of y prime f hat sub y prime. And so if we actually did that product rule in this case, we get y double prime f hat sub y prime plus y prime d by dx f hat sub y prime. Yeah.
So that is that.
Yeah, and so we could just subtract that term over exactly.
Okay.
So yeah, d by dx y prime f hat sub y prime minus y double prime f hat sub y prime is equal to the right hand side. It remained the same. And we added this term over to the other side. Y prime. What happened here? Oh, ha. Now we notice on the right side, it's not quite a product rule, but it is a chain rule
Oh,
of just f hat of y prime. That's why we needed to have that restriction, because you'd have an extra term if it depended on x, I
Yeah.
guess. Okay, yeah, that's sneaky. And so now each side is written as a derivative now, so we can integrate each side to get
Okay.
what the heck? Y prime f hat sub y prime is equal to f hat plus some constant c. And then we can subtract the f hat over. F hat is equal to c. Okay, and this is just a first order ODE now. It's the magic of this simplification. So we Euler's equation is generally like second order. But we get a much easier to solve equation now.
Hey, Phobos is here.
Hey Phobos, you do spot a Femvox fan. Kill that equation. And this thing doesn't have a name. I believe it's Beltrami's identity.
Phobos, we're doing calculus of variations.
Mm-hmm.
It's pretty heavy stuff.
It's cool stuff though too.
It is. It's very cool. So Don, why is this for? You said the other one was second order. You
Yes.
said the Euler DE is second order.
Unless you get lucky with a cancellation, yeah. That is because, oh my god, where is Euler D? There it is. Okay. It's because we're taking. Oops.
Oh, we're taking d dx of f of
yeah.
y prime.
So there's going to be a chain rule in there.
Yeah, I gotcha. Gotcha. I see it. I see it.
You're a local variation, Phobos. You're a delta y. Local variations in your area.
So is this Beltrami identity just kind of like a shortcut, right?
Exactly that.
Yeah. Okay.
And there's an even shorter shortcut. If you have just f equals f of y prime. I don't know if that has a name, but you can actually show that your extremal capital Y is always a line. Funny enough.
Call it the Fem-Don identity.
Yeah, just name it. And that checks out with like the arc length integral that we mentioned at the start. That depends just on y prime, and you do get a linear function out of that.
Yeah. Okay.
Cool. I guess I can pull an example.
So when you took this class, I mean, were there a lot of examples during lecture, or was it mainly lots and lots of theory like this?
Uh, it was built a lot more on examples. Uh,
Oh, okay.
I actually really like the professor's style in this regard. So I'm giving it to you in a pretty like technical way. That is probably not
Well,
how
the
I'd
book,
teach
yeah,
a
I mean,
full-on
the notes
class.
you were just scrolling through, I didn't see much of them, but they look pretty heavy, pretty theory heavy.
Uh, yeah, like at some point you do just have to get into the theory, but usually the start of the
Yeah,
chapters, it it starts with some sort of motivation or example, and the very
yeah,
first chapter it establishes like 6 or so example problems that it refers back to throughout the entire rest of the book.
nice.
Um, and so we actually did that in lecture too. Like he'd say like, oh, an example one that we talked about on this day, uh, like helps explain this thing that we just learned. Equals
Nice.
an x equals an y. Okay.
Your lecturer wrote these notes.
Yeah.
Nice.
He has a Wikipedia page and everything, and like in our department, there's a conference room named after him. He's like a really accomplished dude.
Cool.
Um, apparently, he only like he's like an emeritus professor, and he only teaches classes when he's like about to write a book, from what I heard. So I don't know what he's writing, but
Oh,
apparently he's working on something.
nice.
Um, okay, so I'm trying to find like the simplest kind of non-trivial example is to do the arc length thing, but I want to find a little less trivial one.
Yeah, I read that arc length one on somewhere yesterday. I don't remember where I saw it.
Yeah. And I remember distinctly Dr. Cook had us do that the first day that we did general relativity.
Oh, did he?
Yeah. Okay, so we can do it for a spring mass system. Uh
Yeah, all this is supposed to be very applicable to physics, isn't it?
mhm.
I mean, when you learn classical mechanics and you first learn, kinematics and Newton's law and all that kind of stuff, and then later you learn all the energy methods, and then you realize there's more than one way to skin a cat. That some of the simple problems can be solved two entirely different ways, and the
Exactly.
energy methods are often so nice,
Mhm.
and so much easier too.
Yeah.
And so I'm guessing, I don't know, I'm guessing that this is even a general more general way of looking at that.
Yeah. I honestly I really want to pull up that gravity book that we were using now, because I want to remember exactly how that Lagrangian was defined in physics. But yeah, like everything we've been talking about today, I believe is just like Lagrangian mechanics, basically. Particle
Nice.
gravity. Oh wait, this is that's the wrong PDF. I have a different one. That's the one. Um, maybe the variational principle part. Yeah. Okay. Yeah. Okay. So this was chapter 3 of that gravity book. We
Yeah.
learned the Lagrangian as kinetic energy minus potential energy.
Yeah.
And this is also just Euler's. Wait, they called it Lagrange equation. That's funny. I guess because of a Lagrangian. But yeah, so this is the exact same equation that we just derived through 3.34.
Yeah.
Um, so yeah, for a spring mass system, letting m equals k equals 1, because this is a math problem. Uh, j of y is going to be equal to I guess we're just going to consider generic endpoints. One half. Oh god, I lost my place. Oh, okay, here. Y prime squared minus y squared dx. Okay, and so we can just not worry about the boundary values for now, because actually there's a completely different question, like about you kind of get different solutions depending on the boundary values. But I think this would be a good one to just like go through and apply Euler's equation to. We could do Beltrami's identity too on this, but it's be a good one to find the extremals for.
Before we do any of those things,
Mhm.
can we think about, well, like, where did this come from? I mean, so it's a spring mass system, right? So we have a spring attached to a mass. How did we come up with this?
I believe this is kinetic energy minus potential. It's like this is your 1/2 mv squared. And for spring mass, is it like 1/2
K times kx
kx
squared, right?
squared?
Hooke's law. Yeah, okay. So it's energy, so it's kinetic energy and it's energy in the spring. I see. I got you now.
And so
Okay.
we're minimizing the difference of those energies, I guess.
Yeah.
I'm not quite sure why that gets you the right answer, to be honest, but apparently it does.
Okay, so then this thing in the integrand is what we've been calling L, right? Was it L?
Yes. All right, well, capital F.
Capital F is what it was.
See
Sorry.
you,
Capital
Phobos.
F.
Thanks for being here.
See you,
But yeah,
Phobos. So this is our, so, oh, let me use a different color. So this is our F of x, y, y prime.
mm-hmm.
Okay. So then what is the Euler equation? What does the Euler equation tell us? Is it df dx? Not curly d, right?
It's d by dx of f sub y prime. So we got to do like the two stages of derivatives.
Like that?
Y prime.
Y prime
Yep.
equals, I've forgotten it already. Was it,
F sub
was
y.
it,
It's been burned into my memory.
oh, it's just f sub y, right?
Yeah.
All right, so let's work out what these things are. So first of all, f sub y is minus 2y, right? And f sub y
We
prime.
do have the 1/2 out front to get rid
Oh,
of
yeah.
the two, but yeah.
Oh, so the 1/2 is really inside there. Yeah.
Yeah, I could
Maybe
you could just ignore the 1/2 though, because like minimizing 1/2 times something is the same thing. But it cleans up it's not important.
Yeah. And then the fy prime would be 2y prime. So if I plug those in over here, I get ddx 2y prime equals minus 2y. Stop me if I make a mistake here. So I get 2y double prime equals minus 2y. Yeah, I think this is what I want, right? So I get y double prime equals minus y.
Yeah,
And that definitely looks like it's going to give me the sines and cosines I want, right?
exactly. Yeah.
Okay, so can we just jump to the punchline here? So so do I want y as a function of time? No. I want y to depend on x here.
Oh, I mean, X here really is
Well,
time. It's just a
x,
generic letter.
okay, so yeah, so y of x equals a sine x plus b cosine x. Is that, Oh, and then we have initial conditions, or but we want to integrate this from A to B. So what do we know about points A and B?
So yeah, I left those as vague. What we could do, I just found the point in my notes where we talked about this. We could let um y of 0, we'll keep small b generic because there's an interesting question there, equals 0. So we have the point 0 comma 0 and we have the point b comma 0. Um,
0, 0, and B0.
yes.
So I should write this. Actually, let me see. Should I make this Y here a capital Y now, right? Is this my...
Oh yeah, and so technically from the get-go, we should have made these capital Y's. It's no big deal, but
Oh, because again, this is not, this is F hat. Is it? These guys are
yes.
F hats now already.
Mm-hmm.
Okay. Okay, so Y of 0. So we'll plug in. Now you told me Y of 0 is 0. What about Y of A?
I'm letting a equals 0.
A equals 0. Gotcha.
Yeah. And then b I'm leaving generic. So you get different behavior depending on b.
So let's see. Y of 0 is B, which is 0. And then Y of B is A sine B, which is 0. So
And this is
does
that
this
weird
mean
thing.
does this mean B has to be a multiple of 2 pi? Because I don't want my whole thing to, oh, this is what you said before. It could just be come out to be 0. Yeah.
Yeah.
I guess it would make sense. Everything was 0 if the spring was just stationary, if the whole mass was stationary.
Yeah. And so this is kind of like the example that we were given in the lead up to the Jacobi accessory equation. And so I think there's like a
Yeah.
related thing here where we're finding that capital Y equals 0 is an admissible extremal for this problem. Uh,
Yeah.
but it's not necessarily like what we want. I think in some way the Jacobi accessory equation could help you like figure that out. But yeah, we would require that small b then is going to be a multiple of 2 pi. And I'm trying to figure out what exactly the conclusion was here. I'm looking back at my notes and remembering what we said about this.
Yeah.
Um,
We want to think about what the original equation was telling us,
mhm.
don't we? So A and B are, so little a and little b are x values. So they're positions of where our mass on the spring is.
uh,
So we can
I
call,
think
so
this
you
is
can call
time.
one of them.
Or wait, mm,
Oh yeah, are they
I, I
times?
I wasn't being careful with calling it x versus t. I'm thinking that if y prime is velocity, that's my reasoning. I guess, but potential energy. I think x is technically time.
Okay, okay. So at time 0, and then at some time in the future, we want the position to be 0 again. Yeah, that makes sense. So either it's got to have gone through a full cycle, or it's got to have never moved in the first place.
Yes.
Yeah, yeah, yeah. So I mean, that checks out. I mean, that makes sense, right? And it could have
Hmm.
gone through any number of revolutions, including 0, during that time interval.
Right. And actually, I think you could let b just be k pi even.
Oh, yeah, it could have gone through half a cycle, couldn't it? It could have gone.
Yeah.
Yeah, well, now I'm gonna be confused. It's Oh yeah. In fact, Don, yeah, now I'm coming up against the thing you told me about before where you had to check the great circle and see if the point you found was on the other side of the circle, right? What was that called again? There was some kind of stipulation.
Jacobi's test.
What? Yeah, Jacobi's test. Do we have to do that here?
Basically, yeah, like this is one of the motivating examples we were given for that test.
Yeah, you know why I'm thinking of that? Because if we think of this as a spring and a mass spring system, the conditions haven't told us anything at all about the initial velocity, have they? Like they've said where it starts and where it ends, but I don't know how fast it was moving when it started or what direction.
Yeah, exactly. Like we could have that sine
So it
wave, or
could,
we could
so it
have
could
like
have been going up
double.
or it could have been going down. Yeah.
Yeah, or even
Yeah.
yeah, a
Yeah.
reflection too.
Yeah.
And
Okay. Well, then I think I'm stuck. I don't know what we do next.
I am also I don't know if we actually we seen the textbook. We didn't like we just used it to point out a problem, but we didn't come back and fix the problem. So let me see if he does that in the book.
Oh, okay.
uh, example 4 here is the same problem that we just did.
Oh, yeah. There it is.
Um, if you go through the trouble of forming Jacobi's accessory equation, you get another combination of sines and cosines. Interesting. So what is this saying? So if b is greater than pi, you do have a conjugate point. Because sine of pi is 0. Um, really? I'm trying to figure out what physically, like what that means physically.
I think that makes sense because pi is one half a revolution, right? So,
Yeah.
so depending on where you started and which direction you were moving, I guess the question is like, how long does it take to come back from where you started back to that position, right? It depends where you started from. If you started at the center line of your up and down cycle motion, then it's going to take you exactly half a period to get back there, right? But if you started near up the top of the spring, then either it could take you a short amount of time if you were on the way up, you get to the top and come back to where you started. But if you had been going on the way down, it would take you a long time to get all the way to the bottom and then back up to where you started. And
Oh.
that would be the greater than pi situation, right? Oh,
Oh.
so if you're less than pi, there's no two different ways you can get back to that point, is what I'm saying.
Yeah, I think that makes sense. Huh.
I think that's what they're talking about there. Yeah, like pi is 180, right? 180 or half a cycle is how I'm thinking of it. So
Yeah. And that is really similar to the great circle problem.
yeah,
Interesting. Let's see if there's another like interesting thing that I could pull. Inspired by
Yeah,
blue.
I read that the first person who did some of this was Newton. I think is that who it was? Newton.
Oh, as far as I'm
He
aware,
worked out.
Euler's the one who like kicked this whole thing off.
Yeah, I think no, I think well, yeah, I think Euler was the big name, but I think they said Newton had worked out that problem involving um, a surface of revolution or something.
Mm,
I don't know where I read that. It reminded me when you were scrolling through the six classic problems or something that the book was going to refer back to, and I think that was one of them.
oh, yeah, there is one of those. Um, if you only could
Minimal
post,
resistance. Yeah, this is what I was reading yesterday. This is Wikipedia. Yeah.
yeah. Fire by blue. If you want, you can post whatever you have. I'm not sure if I'll be able to follow it, but and I'll read it maybe like 15-ish minutes. Welcome in. So yeah, I guess maybe he posed problems. As far as I don't know if he. Oh, I guess first problem in the field to be formulated and correctly solved. Oh, okay, he did solve it too. I wonder what his technique was then, because he doesn't really get credit for this.
Hmm.
I guess maybe Euler's just the one who generalized it. I don't know.
And Lagrange was working it out when he was 19. Wow.
Was he? Oh yeah. I was not doing that at 19.
Well, I always say Lagrange didn't have any video games to distract him when he was 19.
That's true.
I was already deep in video games by the time I was 19.
Oh yeah. Um, I mean, actually, what are the other example problems that they give in chapter one?
So this was a whole semester course, wasn't it?
Yeah. Um,
And it wasn't it really wasn't like a physics course, it was a math course.
right.
Yeah.
So, at the end of the day, like it is pretty physical calculus of variations, but there's a lot of non-physics examples that we applied calculus of variations to also. So there's like optimal harvesting in a fish farm,
Yeah.
optimal like wood harvesting for a lumber company. Uh, we could apply it to like chlamydia produces like two different types of cells, and there's like an interesting trade-off between how it decides which type of cell to produce. Um, oh yeah, and it was the final day that we talked about it. Whoever did it won a Nobel Prize for it. They applied calculus of variations to economics.
Hmm.
Um, they basically created a function that is like the social welfare index. Just like in general, how satisfied are people with society, and you can do calculus of variations to try to maximize satisfaction.
Wow.
Um,
Well, when you called it a performance index, that was the first time I'd heard it called that, but it sounds kind of like a economics thing or something, doesn't it? Performance index, or like it's being applied to stock markets or something.
yeah. Um, Shoot, I don't know if I wrote down the name of the actual person who won the Nobel Prize. So I know he said it, but yeah. Oh well, I don't see it. um, What I have on screen now is like if it for a company that's like producing some good, if there's like a cost to storage and also a cost to that scales with like the rate that you produce things, you can get something that looks like equation 1.8 for your functional. I'm not sure why it's y prime squared. I guess just to weight it more. Optimal harvesting for fishery. Okay, yeah. And so I guess we can start to wrap it up. Like, if we do want to do more of stuff like this in the future, which I'm definitely open to, uh, the next thing we'd probably talk about is like ways that we can modify the basic problem that we just talked about. So it'll be like chapter 3 in the book that I'm showing on stream. Um, it's kind of cool. So like we always had two fixed boundary conditions. It turns out you don't actually have to specify those. You can leave things free, and like in that has significance because if you're like, if J is the profit for your business, you don't want your like you want to maximize the profit at the end of whatever your planning period is. Um, so yeah, like we can consider kind of free boundary conditions. I think it'd be nice to talk about like letting y be a vector and bringing some multivariable stuff just a little bit.
Yeah, now that you mentioned that, when you wrote down that example a little while ago with the let's see, what did you have? You had time, you had t, and then you had x and x dot and y dot. So you had a
Mm-hmm.
function of the 5 variables, and I thought, well, we could think of x and y as a vector in that case, and it would be like 3 variables again. It's just
Exactly.
that the vectors would be two vectors with 2 components.
Yeah, and there's like a multivariable form for the Euler differential equation involving like great gradients.
Wow. I mean, it
Um,
looks like really cool stuff.
yeah. Um,
I
it,
think if I'm gonna continue with it, I would want to start reading a book and try and do some problems or something.
oh yeah, that's cool. If you want, I can give you the PDF that I have. But um,
Yeah, when I was looking around yesterday, I found some. I mean, obviously, there's so much stuff online.
mhm.
The what's the one I'm looking at here? Gelfand and Foman, calculus of variations from. I guess they're Russian guys, and it's from the late 1960s, I think. Oh no, 1963. I went to the MIT OpenCourseWare site to see if they
Ooh,
had any classes on it, and they did have one, and this was one of the textbooks they recommended.
oh, interesting.
And I found it on the what's the name of this site again?
Uh,
What's that? Internet Archive. Internet
oh,
Archive.
okay. Yeah, this book is old enough. Is this book actually on it? Internet Archive?
Yeah,
Oh,
yeah.
cool. Yeah, I think it was written in like the 90s, so I guess that makes sense.
Oh no, I didn't find the book you're reading. I found
Oh, okay.
this other one.
Oh, and yeah,
Yeah, but there's so much stuff online. I always want to try and find a book that makes sense to me. Like when we were
mhm.
reading that book, but that Dr. Cook recommended. I think it would be a great book, but boy, it just didn't click in my head. I wasn't like the further we went, the more lost I was getting.
Same.
And by the time we left the class, where we were in chapter 8 or something, but I thought I was just completely underwater. I didn't know what was going on anymore. Um,
Yeah, I think we wanted to go further even, but it became too much for me too.
yeah, yeah. You want to try and forge ahead, don't you? But at some point, you got to pull the plug and say, I got to go back to page 1 and just start over, or find
Yeah,
something else I can try and supplement it with.
yeah. It would be nice to tackle GR again at some point, but probably with a different
Oh yeah,
book.
for sure, for sure. Well, thanks for showing me all this.
Yeah, no problem. I guess we can call it there for the day. If you want, I can
I
even
think
pass you along my homework too.
I definitely followed you but I feel like as we got to the end, I was losing it a little bit. Let's see, what did you have here? Like the Weierstrass excess function, I didn't really know what was going on, and remind me again what the PWS stood for. PWS
Piecewise
extremal
smooth.
Piecewise smooth. Okay, yeah.
Yeah, I honestly, I wish that we had almost done this before the end of my quarter, because I didn't understand a lot of this stuff until I had reviewed it all in preparing for this. Like I was confused for like pretty much the entire class about weak versus strong, and it's not the same. I thought it was basically the same thing as like local versus global, but it's not. Yes, and so it's a little bit weird. You have all these different conditions for different types of minima,
Yeah.
and the space of functions that you're searching is so important. And you can, without realizing it, you can like chop off a whole category of functions when you're deriving this stuff.
Yeah, it'd be cool to look at some more examples.
Okay.
Um, yeah,
I can
I
try
don't
and
know.
figure some out, or like look back through some of my homeworks or something too.
Yeah, for me, I need to, yeah, like the one you just did at the end there with the mass on a spring. You know, I feel like a lot of stuff sort of, I don't know. That's the way I need to see it. Is I need to see something I can tie it to that makes sense.
Yeah, I'm the same way. I was avoiding examples just because like I thought it'd be cool just to try and like get through all like the concepts at least. But yeah,
Yeah,
if it was only the concepts, I wouldn't have learned it very well either. Yeah, with this like spring
yeah,
massing, you could also check like the Legendre condition that we talked about, or the Weierstrass excess function. Although that one's kind of a pain. um, I don't know if it, I don't know what to expect with the Weierstrass excess function. If it would actually give you a weak or strong one.
so yeah, so what is the definition of weak versus strong then? Because I know you told me it was to do with when we looked at H, and we, you know, way back at the start, we said, what did we say? Y prime X, yeah, right here. And it was some, oh, so we were assuming H had to be differentiable. Was that the problem? No.
No. It was just that Y prime is also linked to the same H.
Right, right, right. And then you said later they should be able to be more independent of each other.
Yeah.
Yeah.
Although if you,
Yeah. Okay, I sort
yeah,
of get that. Because where was that then?
that was the
That
Weierstrass
was right.
excess.
That was right here. Yes. And then you said here for all UV near Y prime. And what that does is it makes it feel more like it's a two-dimensional search instead of a one-dimensional
Mm-hmm.
search, maybe. Yeah.
Yeah, I think that's what it's doing. The thing is, if you don't like, if you do let it be like a general U and V instead of H and H prime, I don't think you can get to the Euler DE. So if you want a strong minimum and you only ended up with a weak one, I'm not sure if you can fix that. Maybe there's something that you can do, but I don't know how.
That was cool. There's a lot of stuff you told me today that I'd never heard before. So thanks for telling me that.
Yeah, uh I thought it was interesting. Like in like I know that you don't remember it too well, but when we learned about it in GR, like we skipped over, like we only did the very basic stuff for calculus of variations, and I didn't realize that there's all this extra like all these extra considerations to it also.
Yeah.
Like we did just the
I
Euler
guess
DE.
it's like anything in math, isn't it? I mean, if you pull it off and look under the hood, you can just go as deep as you want.
Mm-hmm. Yeah,
Very cool.
I guess in physics you always have stuff that's clean enough that you don't have to worry about it.
Yeah.
Okay,
All right. Well, I guess I'll head out and let you get to some general math.
sounds good. Thank you for doing this.
Yeah, no problem. It was fun.
Yeah. All right. See you.
All right. Yep. See ya.
Okay. Round of applause for Fembox for putting up with me basically trying to speedrun weeks worth of like graduate level math. Give me 1 minute to kind of like switch things over here. I'll post the image of this into the Discord too, just for future reference. Ooh, what song? I had this song stuck in my head yesterday. And I was like, ooh, I should use this as the seed song for today's playlist. Oh. Oh wait, never mind. Okay. Wait, what the hell? I see an Eminem song in the pipeline. That's I'll keep it in there because it is a banger of a song. It's not very related to this though. A little quieter. Okay. Let me change my YouTube information. And Fire by Blue, if you're still here, let me know. Right after this, I can take a look at what you posted. Let me grab... How do we get export image, right? Copy. Okay. Let me open up what Fire by Blue wrote. Oh, no, I didn't hear that at all. $10. Okay, so this is what Fire by Blue posted. Okay, the title list is already very heavy. Can I make this bigger? There we go, that's what I want. It is only 2 pages, as promised. Oops, it's not the zoom that I wanted to do. Okay, so 1915 proposed general relativity describing space-time fabric of the universe, which shows properties of curvature. Framework at the time required solutions to its fields equations. Also use vector and tensor mechanics onto Yapping connection to describe transportation in the framework through the Levi-Civita connection. Preserves angels. You gotta preserve those angels. Twisting of the space-time manifold. I'm already very out of my depth here, but we can just keep on reading the words at least. Einstein set out to make its framework general relativity. Hasn't done so to rework gravity. Highlights motion, which is fun. path of spacetime appear to bend along with it. Okay, Schwarzschild provided the first most simple solution to Einstein's field equation. Okay. Solution later became the framework for black holes. That's what we call it the Schwarzschild radius. Oh, I did learn Schwarzschild is apparently German for black shield, which is like so perfect for the dude who theorized about black holes. L.A. Cartan worked with Einstein to create Einstein-Cartan framework for GR, which includes torsion, twisting of spacetime. I remember Levi Civitas having something to do with like those gammas. The Christoffel symbols. I don't remember that well though. Christoffel symbol, yeah. Okay, yeah, I don't know if Fiber Blue is still here. Um, I think I don't. I've barely studied general relativity, and I've studied zero quantum mechanics. So I feel very lost. It seems like full on GR and like full on quantum. What is the Dirac equation? Relativistic wave equation. Delt D with a slash through it? The 4 gradient in the gamma matrix? Oh god. I don't want to know. I'm gonna get PTSD from Einstein notation. This is gradient with a dot over it, by the way. This isn't your normal run-of-the-mill gradient. I don't know what it is. It might be the same D with a slash, maybe. Oh, actually, yeah. It definitely is that. Huh. So yeah, this is very succinct, I guess, and assumes a lot of the reader. And I think I'm not the intended audience for this. Unfortunately, I would love to understand this, but a lot of this is a lot of things the author is saying here is news to me, and I don't really know what it means. So I might just leave this here. The issue is I don't know what to do. Like I spent the last year filling the spare time with homework, and now I don't have that. So uh I gotta figure out something to do now. Back to the Warren Blue Book? That's a thought. Depending how much suffering I'm in the mood for. Divgrad curl, that's true. Um yeah, it won't be today, but like I remember Slim for a while was working on like perspective geometry. And I'd love to find a topic like that isn't very heavy. And that like people who like don't know calculus, for example, could get into and follow along with too. So I would need to find a topic like that, but I'd like to find something like that to help fill the time. I don't know of one offhand, but um More in Blue Book, divgrad curl. The Blue Book would be a good idea because I really did just skip over the rotational stuff. Oh, I didn't write that book down. It might have been Winklebot. I do want to learn some graph theory. I want to. Actually, you know, that's something we can do. Like, I want like a specific type of graph theory book that may not exist. Like, I want something that's on the applied side of things. Graph optimization, like that sort of thing. Algebraic graph theory. Trudeau. Oh, right. Yeah. Prime Minister of Canada. That I remember it now. I made that joke. Combinatorial spanning trees. I mean, I don't know. Spectral, like that's the type of thing that I really want to learn about with graph theory. Because this is actually really sick, and like graph theory has a connection with like PDEs. And it's really beautiful, but I don't really understand it. So yeah, that's let's see what this thread says. Wait, can you graph theory your way around a Sudoku? That would be interesting. Sudoku graph theory. Vertices represent the cells of a playing Sudoku puzzle. That makes sense. Pre-coloring extension. Oh, this is kind of sick. Photograph has into the fourth vertices. That's true, Lucas. There's that like hundreds of pages book that whoever wrote on why 1 + 1 = 2. Ooh, click is a graph term? That's funny. Getting into programming lately, Python is so fun. Testing out with classes? Ooh, cool, cool. Python is really good to know. It would fit Fembox. I'm definitely am down and would be excited for divgrad curl. I don't know who else would be is the problem. But I mean, if it was just you and me, I'd be happy. You just say that Slim said that he'd be willing. Um, hey Zach. Yeah, and so I'd be down for that. But I'd be down for another subject. It's always hard to like choose one. It's always the problem. Yeah, I don't know. I can definitely feel graph theory being in my future at some point. I don't know. So I can also see doing something that's kind of like out of left field to like astronomy. I don't know. There's a whole world of possibilities. And graph theory is not easy, Lucas. That's true, Zach. I do really like the book that you chose. I think that studying it through special relativity is the coolest way to study E&M. It's so cool that the world that we live in works how it does. Yeah, I could ramble about it, but like just how like it's just like you just start with electrostatics and you just add in relativity and you get all these amazing like behaviors that is so foundational to how like our technology works today. It's so different compared to other fields of math. It is like the classic first graph theory problem was the seven bridges of Königsberg. It was solved by Euler, and apparently when someone first asked Euler to solve this, I learned this from Ian Stuckey. Euler said that this is not even a math problem. Why are you asking me? uh, he said a lot more like elegantly and in more words than that. But that was like the basic message. And yeah, Lucas, the same in 2 days about exactly that. Yeah, Zach, I learned that like recently because it was when it was that day recently in your stream you're being asked a bunch of graph theory questions, and I jokingly asked about this problem on screen, and Ian Stuckey posted a link to the letter that Euler wrote about this problem. Basically, it's in 2 days about exactly that. Yeah, good luck, Lucas. Yeah, I don't know if Zach has settled on like a day to meet, but Zach is going to be doing a reading group on electricity and magnetism, which is going to be super cool. And Dr. Gold / actual education is actually teaching an undergraduate college course on E&M over summer. I don't know when it's starting. I assume very soon, if not all. Well, I haven't seen him streaming it. I assume he's planning to stream it though. My opinion, graph theory is barely math. That's on my level. Yeah, it's included in math, but it's it's not like other parts of math. It's a type of discrete math, and discrete math in general is kind of different. It lives in its own world in my mind. You can still relate it to other parts of math though. Like we were just talking about a book that talks about algebraic graph theory, which is like abstract algebra plus graph theory. Thursday. Tuesday is a math review. Ours, ooh, that's a good structure. I know like Winglebot in particular was saying that he doesn't have like he might not have like the prereqs, but I'm sure that you'd be able to like help him out with those as needed. Should getting into physics race attempting to. I mean, if you think you're interested in it, you should try it because I did not like physics for my entire life until a few years ago when I did the E&M reading group. At first, Phobos and Ian Stuckey were there, and then Femvox joined, and for a lot of it was just me and Femvox. And I fell in love with electricity and magnetism as like a topic. I still don't like mechanics really, but it is important. And I've kind of, it's not very high on my priority list, but I would love to learn about like statistical mechanics too. Quantum mechanics. It really is Fembox. Big single back is like the small things interested in very big physics questions. Yeah, but if you want to tackle those big questions, you kind of need to learn the smaller things first. At least if you want to do a good job of it. Yeah, there's a lot of people who really want to talk about quantum mechanics, but they don't know that they haven't actually studied it, and I haven't either, so I tend to not talk about it. What's Yev's jokes? My sister placed a bet with me I couldn't name a state that starts with I other than Illinois. Now I owe a lot of money. Hey, G-Hive. You're always coming in hot with the dad jokes, and I love them. Okay. I need to find something to fill in the time here. Maybe we'll do some mechanics problems. If someone wants to ask something, please do, because I want to keep streaming, but I don't have a particular thing that I want to stream about right now, so I'm just kind of looking through my mystical folder with PDFs of textbooks. There's a lot of options, but we could do some rotational mechanics, or try to. Probably fail at it. Let's start with torque. SR instead of GR. Doesn't Morin have a book on just at SR? I wouldn't mind doing that. I don't have it offhand. We could try and quickly search for it though. For the enthusiastic beginner. Stuff like quarks as well. Why not set up a potential model for a smaller type of electron? It's one of those things where like you're getting to the forefront of physics where like there's no reason you can't do that, but why would you want to? You need to start by trying to explain some behavior that existing physics can't explain. This is a good song. Fleetwood Mac. There's no question that's too small. The integral position also have a physical interpretation. Ooh, okay, yeah. So you're asking like, so normally take the derivative of position to get velocity, and you're asking about the reverse direction. Yeah, and Zach is right. Maybe displacement, depending on how you're doing things. These are my notes that I wrote for the Cox variation stuff for Fembox. Let's just make a new page. So you need to be clear about like what you're actually measuring here. But if this axis is time and x is position, and so it like x's position as in like distance away from home, from the origin. the fembox lectures. Let's say you start at the origin and you take any like arbitrary path. So like maybe we even go down here. That's true. We do need a fembox stream someday. Yeah, I mean, you're allowed to have a negative position. There's nothing inherently wrong with it. Oh no, yeah, that's fine. So like, if you think about like a spring with a mass, like it's all about how you define things. Um, maybe like when the spring is most compressed, the mass is here, and when the spring is most stretched, it's like all the way out here. It's pretty common to say that the zero position is like right in the middle of those two. And so like on this side you have negative position, and on that side you have positive. You could also define zero as like from the start, but I would think about like the physics first here, and we're just attaching coordinates to that physical situation. And you're allowed to place the origin anywhere you want. Like coordinates are just a thing that humans a way that humans describe the position of things, I guess. And so yeah, this graph is just of some strange object that's moving in some random way. Basically, and remember, this is distance from the origin. So like, this is when it's the farthest. If you think this is one-dimensional movement too. So if this is our zero position, and this is x, the particle starts by like moving to the right. It comes back around for a little bit, and then it keeps moving away. It reaches the farthest away position. Oops. Oh, I didn't mean to do that. Reaches some position as far away as it can be, and it kind of quickly comes back and goes to negative, and then it returns back home. Oh, is it? I put it on radio for Sweet Dreams by the Eurythmics. It's kind of making some strange choices for what's related to that. So yeah, no, I'm enjoying it too. It's just a little all over the place. So if your x is defined like this, which is, I think it's the typical way to do things, because if you take the derivative of this x in time, you do get velocity out. And so the question that you asked about about like integrating instead of derivative, from some time 0 to another time, let's call it t1. Why not? This we would call displacement. So d, right? Yes. Is it? No. Wait. Yeah, what is a meter times a second, though? Yeah, it's total distance traveled. There's a subtlety here, though. Um, we need absolute values. Because normally when we care about total distance traveled, this negative distance we want to count as positive. Because, like, again, negative position is just, it's kind of artificial. If we want to measure distance traveled, that should still count, the same as anything that's positive. So we need to take the absolute value. Um, I think this was right. I'm going to Google because I'm sure you're not the only person who's asked this question, and I'm worried that I'm saying something slightly wrong. I want to say this makes sense to me right now. Yeah, that's what I'm worried about, Fembox. If I... that might be final position, though, not distance. That, like, displacement, maybe. I don't know. Absement. Oh, I forgot that. Yeah, they did release a... Is it specifically Freddie Mercury or Queen in general? I remember hearing about that. Okay. Focusing on Freddie Mercury. Measure of how far away and for how long. Absement is a portmanteau of the words absence and displacement. Oh, cool, cool. Huh. Okay, yeah, so it's nothing that you would have heard of, I guess, the integral position. I must have said something I must have said something wrong, I think. Uh, not to be confused with basement. uh, it's like distance traveled, but it's kind of weighted by how long it spends at each distance. It's like if an object goes to a spot and stays there, then that keeps then even though it's staying in one place, that's still counting in this integral, I guess. Um oh, look at this. Okay, starting displacement, velocity, acceleration, jerk, jounce, flounce, pounce. I haven't heard those last two. Then we have absement, absidy, abceleration, abcirc. Oh, they're getting crazy. Power, energy, actiturgy. They use Aleph for some reason. Why? Absement, um, they explain it there. It's a combination of absence and displacement for some reason. That's the answer to Lucas's question. I've heard somewhere that physics has a lot of catching up to do for math, since there exists so much more math that physics currently applies, or then physics currently applies. I mean, I would say physics isn't obligated to apply everything that math creates. Mathematicians are kind of generally, they just kind of do their thing without caring or worrying about applications. A lot of them do, not all of them. Actually, there's a give and take. Sometimes a mathematician invents something that a physicist later discovers is helpful. And sometimes a physicist asks a question that a mathematician then answers. So there's a give and take. But I wouldn't say that just because a mathematician invents something, a physicist has to use it somewhere. For someone to say the integral of work is energy. That's a, yeah, no, that the integral of work is exactly the definition of potential energy. That's how it's defined. Well, we should be. So there's an important difference with what you're saying, Lucas. Work is the integral of. Oh, I'm sorry, maybe not energy, or the integral of work is energy. Shoot, no, I'm saying this wrong. Energy is change in work, I believe. This will tell us. No? Wait. Wait, what the hell? It's power. Wait, where's the... Okay. Why can't... I should know this offhand. Work is force times distance. Okay, yeah, okay. Work is change in potential energy. Okay. I'm not crazy. And I think that is the work energy theorem. That's the issue between work and energy. It's just a simple, like, subtraction. You can define work as the integral of force over distance, which is very different from integrating over time. You can convert a distance integral to a time integral, but you get like a chain rule thing. Some mathematicians only like their work if it has no worldly purpose. Exactly, yeah. So you don't understand the work being the integral of force bit. It's a it doesn't have to be. So yeah, let's talk about the intuition. And I normally go to a multivariable explanation for this, but it's really not necessary. I think MJ. I don't know who AAL is either. Like, I think about the no, never mind. Okay, so let's say you have a hill That's the crappy hill. Let's say you have a hill and a Weird Al. Oh, eat it. Yeah, yeah. No, this is the original. And let's say the hill has height h. And you are carrying a ball. The World Cup is happening, so it can be a soccer ball or football, depending on your persuasion. It's the same size as your head, I guess. (5-1) Netherlands versus Sweden. Ooh, congrats. Okay, and so I'll even go against my American instincts, and I'll call this a football. Let's say it has a mass m. You are doing work to bring the ball with mass m from the bottom of this hill to the top of the hill. So, if we define the bottom of the hill as like y equals 0, and the top of the hill as y equals h, I'm using y to mean height. It's just put position. You could also use x. At the bottom of the hill, the potential energy of the ball is 0, because it's in general the formula is mass, gravity, height, and so the p at the bottom is 0, and the potential energy at the top is mgh. And so this is a gravitational potential energy. So when you bring the ball from the bottom to the top, you've changed the energy by mgh minus 0, which is just mgh. And that's the amount of work that you've done against the force of gravity. Exactly, yes. And so gravity is trying to pull the ball down, but you're pulling the ball up. I guess equally as hard. So, like, yeah, you do work against another force. I mean, you could do negative work, which goes in the same direction as a force. That's allowed too. Again, that's just like, there's no reason you can't have negative work, basically. That would correspond to you bringing the ball down the hill. Yeah, work is kind of tricky. Like, that's like the basic version of it. It can be a little bit weird to apply it to more complicated situations, so... This is a good song. You say 1-2-0. Ooh. Okay, so the integral stuff. Thank you, thank you. Trying to think of a good way to explain this. Okay, so at its core, work is force times distance. In this case, gravity only acts downward, so we only care about like this vertical distance. Because we're doing it against gravity, so we only measure distance vertically. And for this situation, the calculation up here is a fine approximation, but we assume that the force of gravity is constant. Technically, it's not, like gravity is weaker the farther away you are. But like here, like the size of a hill is barely a change relative to like the strength of gravity. So it's fine to call it constant for this like simple case. But there are other situations where like your force is not the same at every point, and it is significant. So maybe let's use like if you have like a positive charge here. I mean, you could talk about a black hole, but it's really like you don't need to talk about a black hole specifically. It's more about like the scales that are involved. Like the Earth is huge, and the size of a hill is negligible. So if you, it would be significant if you were like launching a satellite into space. If you want to calculate the work, then you definitely need to account for gravity getting weaker, because that's going to make a big difference. And so yeah, the example I was going to use is if you have like a positive charge. So the only basic for physics. I mean, yeah, that's why in this like toy example, we, you know, we kept it simple, but let's the physics playground, yeah. For this example that I'm talking about here, if you have like a positive charge that's like repelling other positive charges away, let's say, so this charge is staying still. Let's say you have a second positive charge, and you are physically pushing you don't feel that very happy about it, but you're physically pushing this charge like, you know, some distance like this close, let's say, and the charge that you have is being pushed away by that positive charge. Not only that, but it's pushing away harder the closer you get, because like if I drew this a little more accurately, close to the charge it repels the strongest, and farther away it repels weaker and weaker. And so this is a situation where you would need to break this path up into really small pieces, and add up the force that you're experiencing on each of those pieces. And that's exactly what an integral does for you. Hey, Suckno. So the work here would be the integral. Okay, so when you're at the start, the force from this charge is very weak. But as you push the charge closer and closer, this charge over here is pushing back stronger and stronger. And so you need to account for that force changing as you get closer. Okay, yeah. And so the way you deal with that force changing as you get closer is you do your calculus thing. Take this up as cut it up into a bunch of pieces. Solve the problem on each of those pieces and add them all back up at the end. That's what integration is. So if this is your 0 point and this is like x1, you'd integrate from 0 to x1 of the force of the charge, which it's really similar to gravity. Oh, what's the name for that constant? Why can't I? Oh no, this is terrible. Why can't I remember? Is it C? What's the constant in Coulomb's law? Hey, thank you, thank you. And let's say these charges are both Q. Or no, let's say that they're both positive 1. Even easier. Plus 1. So it would be K times 1 times 1 divided by... Actually, I made a... 0 is a bad idea. 0 is the one number I should not have used. Let's say... let's pretend that 0 is over here. The final point is x2. The initial point is x1. Yeah, that's... that's the problem. Divided by x squared. And then the distance is dx. Because remember, we're... each of these things has a width dx. These little intervals here. And so, like, this total distance here becomes an integral over x, basically. Yeah, Felix, that's what I was getting mixed up with. The 1 over 4 pi epsilon naught. And so, like, what we actually, like, this isn't the real definition of work. They usually that's usually what they teach you when you first learn about work. The integral version is kind of the real definition, and it simplifies down to force times distance if your force is just a constant number. So I hope that part makes sense. There is another complication that we could add into this, which maybe I shouldn't like get too deep into because you haven't learned that yet. But like if you notice on the Wikipedia page, I'm looking specifically at the first line for that integral. That's a vector f, and that's a vector s, which represents a path. I wouldn't worry like too much about this, but what that's saying is like you were pushing the charge just in one direction, but you could have also like done some crazy path if you cared to. I don't know why you would. But you can kind of extend this idea to be for any like 2 or 3 or whatever dimensional path also. And so that's why you get some vectors involved in things. As it turns out, though, even if you did some crazy path, as long as you start and end at the same place as in this problem, it would come out to be the same, though. Kind of interestingly. So if you still start at this distance and you do some weird thing, as long as you end at the same place, it's still the same total work. Funny enough. Alien calculus and resurgence theory. I know nothing about them. Alien calculus? Yeah, and that's another way that integration gets involved too. But you haven't. I don't think you've gotten that far in calculus, so I don't want to get too deep into that. I brought up a page tells us about resurgence theory. I'll look at it in a second. And it became the same as the average. I drew it in a deceptive way. I wouldn't think about averages. You could have also done like just a curvy path like that, where the average isn't 0. It's more because like the force only pushes away in a certain direction. So you only need to worry about the part of the path. Like if you do take this path, you only need to worry about the parts of the path where you're actually like going against the charge. Like right at this point, you're not pushing directly against the charge. You're kind of pushing to the side of it. So you're not necessarily actually doing work against the charge because you're not pushing like closer to it at that instant. Okay, what is a resurgent function? What's the question, Sword? Similarity of divergent series treats analytic functions with isolated singularities. Huh. Asymmetric analysis, differential equations, perturbation theory, quantum field theory. Oh, what is this? What is this? Oh my god. C delta direct sum plus R hat subs omega? No. Whoever wrote this is a jerk. You can't just drop this. Omega continuable germ? Yeah, Tussulus. I don't know this stuff. Yeah. Um, the force of the charge repelling a charge depends exactly that. Like, yeah. You said it well, Lucas. This sounds kind of familiar. Don't remember exactly what's up with it though. Sword. Locally weighted regression. Another Queen song, yeah. It's a good one though. Let's see. Locally weighted regression. Yeah, asymptotic series are kind of like Taylor series, but they're a little more general. Right, Sword. I know like that kind of general definition for regression. The locally weighted part, I don't know what that means. Model-based methods such as neural networks and the mixture of Gaussians use the data to build a parameterized model. Training models used for predictions, data are generally discarded. Memory-based methods are non-parametric approaches explicitly retain the training data. Memory-based method that performs a regression around a point of interest using only training data that are local to the point. Huh. That's kind of cool. Sage works. Hope you're doing well. Sorry. Hey, Sage. There you go. That's the greeting that you prefer. We're going 5 steps further. Sounds good, Lucas. Thank you for the questions. Hey, Roxra. Generally allows you to fit a straight line. Local allows you to fit through any curve. You can do regression in general with other types of things. That's what machine learning basically is. This looks like locally weighted regression looks like regression, but you only restrict yourself to data around your point of interest X. So we'll use linear regression just to keep things simpler. But your entire data set might look something like that. Let's add a few more points. And if you run a linear regression on the entire data set, you would get this or something like that. Let me do that in green also. But if you do locally weighted regression, let's say you have to choose a point of interest. So let's say like our x is right here that we're interested in to make a prediction. It looks like we would do regression, say, only with like these points here, and so we'd have to define like what the neighborhood is, or like how big this width is, but we can do that and do regression only with these points inside of this interval. So you actually get a line like that to predict with. Why is the second difference 2a in a quadratic sequence? I don't know what that means. I'd have to look it up. Hey, Kpars. Yeah, I mean this is basically like a kernel thing. What I don't understand is the loss function. You multiply the loss function by a weight. I'm confused. How does that put emphasis on the local points? Oh, Tussless, I have no clue. I'm sorry. Brookshire, I can look into that. I just need to Google what a quadratic sequence is. I want to keep talking to Sword and hopefully resolve their question, though. Multiply the loss function by a weight. The further points are from the center of the kernel, the less they will weigh on the predictions. Yes. Since some local points by lowering the punishment. Oh, yeah. Oh, Dr. Meanfield, it's been a minute. Hope you've been good. Yeah, so the loss function, okay, so it's been a few months for me since I've done machine learning stuff. The loss function, like, that's the thing that you're trying to, like, minimize, right? Yeah. Okay. So yeah, loss is how you're measuring error. And as Dr. Meanfield and Kpars are saying, you engineer your loss function, to basically you're reducing the penalty for error on points that are farther away from each point of interest. And Tesla, yes, sorry, you're asking about things that I really don't know about. Okay, yeah, it's like something like that, right? And so if that's your normal loss function, oh yeah, we usually square it, right? Hmm. Yeah, I also want to crack on my notebook to remember exactly how we were writing in my class, but Yeah, you probably use like a Gaussian. Yeah. Oh, okay, yeah. Tussles, you can post your integral if you want. I'm pretty sure you're trolling me though, and you're gonna post some crazily difficult one though. So I think my answer's probably gonna end up being no, but you can post it. Some constant I'll call sigma. Um, I've had that experience too many times. Rook's raw. One times x to the 1d1. I'm gonna pass. Thank you though. Um, how that results in a straight line at point x. It's because I wonder if this is just like a procedural thing, because like by this point in the process, we've already decided to use linear regression. We're trying to find the line that minimizes the error. But error is whatever you like. You can define error however you want. Like the fact that we're using linear regression and measuring error in this way aren't actually that related. Like you need to relate them to actually like go through and solve it, but um we've separately decided to use a line and to use an error function that emphasizes the local data to that point. So you could do the same exact thing if you wanted with like a parabola or sines and cosines, I think. Can you show that for any lambda greater than 0, the variance of a ridge regression is less than that of the OLS, but has a biased expectation? I forget what OLS is k-pars. I do remember like this is what's called like the regularity constant or something that lambda is to penalize the complexity of the model. Ordinary least squares. If I dug through my notes, I think we did that in class. I'm just a little bit rusty on this machine learning stuff. So find if I apply calculus to AP Physics 1 problems where it's strictly forbidden. I think for the free response questions, I don't, you're probably not allowed to use calculus is my guess, but I don't know. Maybe not. I would hope that they'd be explicit about that. In campers, I'm happy to like think about that more. I want to keep addressing Sword's question, and then Rookser also asked a question. Fenlux may have answered it though. Parameters come out such that they fit the local point the best. If I expand the sum, can I prove? No, like just this piece is ordinary least squares. I feel like I'm still writing it slightly wrong, to be honest. Um, but yeah, like, the thing I'm trying to say is that, like, we've already decided that our line function, I guess h of x, is going to be like some constant times x plus some other constant, which is, it is? Okay. like we've already decided that H is going to have this form. The only task is to find C1 and C2 that minimize whatever our loss is. That's where this function comes into play here. So and like the thing I'm trying to say is that we could have chosen H to be anything else and do the same process. Well, maybe not like you should choose like particular types of functions that are nice, but that's basically what ridge regression is. Or kernel ridge regression, whatever it's called. But yeah, your choice of model, in this case a line, is a completely, well, it's a very different choice from how you measure error. You don't necessarily go from this to this, I don't think. I did do a Mecha Chameleon stream yesterday. It was a really good time too. I'm sorry you missed it. Yes, and we've engineered an error function that cares pretty much only about local points. Okay, K-Parse, thank you for confirming that. Yeah, so I know you can do it with like polynomials. I think of any degree even. It's probably not that difficult, but like I don't know offhand how to do it. Well, I mean, I'm not sure what you want to prove because what you just said there that it will fit it locally the best. It's a matter of opinion, unfortunately. Like there isn't one right answer. So I'm not like it's kind of. I feel like the question needs to be more specific than what you've written in chat here. Although even if it is more specific, I'm not sure that I could. I'm a little too rusty on this to be able to do manipulations with it. Yeah, but like, there's no reason you have to use a Gaussian here, for example. There's a million other things we could have chosen that would also accomplish local weighting. Um, I don't know offhand, but this is something that Google can answer. Here we go. Uh, the double factorial of a number is this crazy thing with the gamma function. um, yeah, I think K-Pars is saying is that's a good idea. What K-Pars is saying, like showing that the error for this local weighting is going to be like for the particular point X that you've chosen, the error from local weighting is smaller than the error for global weighting. Or, just like the global model. That if you're being asked to do something, that's probably what you're being asked to do. Like compare the two errors and show that it's an improvement to do local weighting. Hey, George Lopez song. I do want to move on and respond to Roxra and I almost said Mecha Chameleon because I read Roxra's comment again. And K-Pars. Yeah, I would say like don't worry too much about like why is this a Gaussian? People in this world just really like Gaussian functions and they use them at every opportunity possible, but there's nothing particularly special about it. So I wouldn't worry like too much about that piece if that's what you're stuck on. Gaussian functions are pretty great and I do like them, but like yeah, there's a lot of choice in this. Okay, so Roxra, do you want to talk about quadratic sequences still? And then we can return to machine learning stuff with what K-Pars asked too. If I can figure it out. Okay. K-Pars said that. Gauss-Markov assumptions for linear models seem the error to be about normally distributed with constant variance. The second difference? Is this like a discrete derivative type of thing? So I can automatically see, take two derivatives of this, you get 2a. But if we have a quadratic sequence, I don't quite know. How do we define a second difference? Doing AP Physics 1 linearization. Oh, okay. Yeah, I need to look at what Femvox said. One, 4, 9, 16, 3, 5, 7, 2, 2. What quadratic function? And Femvox saying something about making L's and cutting into strips. You might say ax squared plus bx plus c. That's what I was thinking, Zach. That'd be something like that. But I think Also, the x with a b should be x plus 1, x plus 2, right? Yeah, okay. I've not done very much machine learning. I know the basics of it from a class I took a few months ago. So yeah, what Zach is saying is where my mind initially went with this problem, which is like the first difference generically should look like this. It depends on the class stored. I think in general, you usually just it's usually more important to know the algorithms and the concepts. Oh, this is a generic version of the first difference. So we found this 3 by doing 4 minus 1. I don't know what quadratic makes this sequence of numbers. 2ax plus 8. Oh, for the first difference. Like there's some quadratic function that created this sequence of numbers, and this is taking the same quadratic and subtracting 2 consecutive terms, which is how we got this 3 or this 5 or that 7. And so whatever result we get here should generate the results for the second row. All right, so the ax squareds cancel. Okay, I can't explain this without what quadratic generates these? I need to figure that out, or else I can't do this. If this x equals 1, x equals 2, x equals 3, it's just x squared. Oh, sorry. Okay. Okay. So we have x squared. What we did is we took x squared, we plugged in x equals 1 to get this, x equals 2 to get that, x equals 3 to get that, and so on. The first, and so all of these pairs of numbers are separated just by like a difference of 1. It's like from 1 to 2 we go by 1, 2 to 3 we go by 1. So we can generically write the first difference as the difference of 2 of these terms up here. And we know they're separated by just 1 x apart. So if this is generated by x squared, we can get the first difference by looking at x plus 1 squared minus x squared. Or you can give this like, if f of x is your generic quadratic, what we're looking at is f of x plus 1 minus f of x. Yeah, chasing after every proof is a recipe for discouragement. Yeah, this is just a derivative, Femvox, like a discrete derivative. Roxo, this is not just f of x. This is just some other function. But yeah, on this line, if we expanded this out, we would get what, 2x plus 1? And if we plugged in x equals 1 here, we get 3. And oh, look, 3 is the first one that we get over here. No, it would be 6a, right? For cubic, third difference. So I don't know if this is helping you connect the dots, Roxra. I'm still trying to figure out what... I guess the second difference, we do the same thing again, but with this. We would do 2 times x plus 1 minus 2x plus 1. 2x's cancel. 3 minus 1. Oh yeah, it's 2. Look at that. Oh, cool. K-Pars. Mr. Blue Sky? Yeah, that's a good song. Induction? I don't know if we need induction here, Peach Tea. You could take an induction approach, I think, though. To actually, like, prove these sequences. Okay, so... n divided by x plus 1. Am I reading that right? Okay. I'm not sure what you are saying, but this is basically what a first difference is. Like, it's f of x plus 1 minus f of x. It's a little bit confusing because we're saying x. Like, it might be more familiar if we said n. Because we're really talking about a sequence here. Exactly, yes. That's perfect. Well, yeah. That actually wait. That is a little bit backwards. You said minus 1. Sorry. I misread what you wrote. I'm sorry. The only difference is I would change that minus to a plus. And it's a little cleaner, I think. This would still get you something like the right answer. I think you get the negative version though. But yeah, if you make that a plus, I say it's perfect. You could make it a minus and just reverse the order though. So like, you're not wrong. It's just knowing what you have. Still going. Probably not for much longer, Stuki, but we got some good questions in queue here. So are you addicted to math? Yeah. And so second difference, just repeat the same exact process with the result that you just got. Like, you know, it's the first difference of the first difference. Okay, well let's keep working the example that you said. So we found that the first difference, or let's find the first difference for your example. That's what you wrote, right? Besides the plus. Yes, okay. So I'll expand this out and I'll do it step by step. 3x squared. 3x squared plus 6x plus 6 minus 3x squared. Um, not quite. I think there should be a way to do it directly from your original function. I would need to work it out though. I'm not sure offhand. There's definitely a way. What you wrote, it's just gonna be, well, I don't know what that's gonna be. I can tell you the way that I know for sure will work, which is doing it in 2 steps instead of 1. There is a 1-step way. These 3x squareds cancel, so we get 6x plus 6. That's our first difference. Oh wait, I see what you're doing now. Sorry. Uh, almost what you wrote. Okay, um okay, so yeah, to do it the step-by-step way that I'm saying, what you wrote is perfect. Just remember your parentheses. Um, and this will end up being 6. For a quadratic, it'll always be a constant. In general, it could involve x still though. In sword, there's a lot of options. It's that's a whole area of choosing the right error function. Um, I would just go to Google for that because I don't know them offhand. Yeah, so um, we could do it. We could start. We could use this to go directly to the first or to the second difference. Um, so we're taking this as our base, and we're again not all of it, but a good amount of it. I'd say potentially even bigger is what model you choose. Linear, um, polynomial, sines and cosines. Oh yeah, a 2K parse. Okay, so everywhere we see an x in here, we make it x plus 1. Minus the original. And I think that's really close to what you wrote. Maybe just some parentheses are slightly off. But in theory, if we simplify this, it'll give us the same thing back. And let's actually, let's make Wolfram Alpha simplify it for us. Yeah, this is just like this is basically the Euler method for numerically approximating a derivative with dx equals 1. Oh, I wouldn't worry about the numerical method thing if that's what you're whatting about. We're basically you're secretly doing an approximation for a derivative. I don't think you're actually you learn this through physics, so maybe um that's why you would learn this, I guess. Look at that, 6. In time series modeling, they frequently call difference models integrated. I'm not sure, K-pars. I don't remember seeing integrate in the context that you're talking about. I'd have to look into it. Um, and I think we're nearing the end of this question here. So yeah, so Roxra, if you did the same exact process that we just did together here for a generic quadratic, you would get just 2a. Or the first one would be something else, but the second difference would be 2a. Sum it up for like 4x squared, for example. First difference, 4x plus 1 squared, perfect. First difference is perfect. That's the second difference looks good too. Not verifying every last number exactly. Well, you still need the parentheses for the second piece. For the, it should be minus parentheses 8x plus 4. Other than that, what you wrote is perfect. Stochastic calculus class? That'd be really cool, PeachD. I would love to learn about stochastic calculus. I don't have any plans to do it specifically, but that'd be cool. Okay, so in Felix, it did make a cool like drawing with the with like a geometric interpretation to the pattern here too. This has a connection, I'm sure, with like triangular numbers or something, or rectangular numbers, or like there's certainly some kind of like number theory thing that's involved here. But I think of it in calculus terms as this is like a derivative, and it's not a coincidence that the second derivative of the continuous function f of x matches with the second difference of this. Yeah, I looked at it. I'll show it on stream though, because it is like a cool picture. Okay. So yeah, I guess you're starting up here, with like x equals 1 for the example that Femox used, and each time you go out a layer, you're adding 2 more. That seems to me that's the second difference, though. I also expect that to be the first difference, what gets added to each layer. Where does the first difference show up here? 3, 5, 7. Oh, wait, no, this is the first difference what you've drawn, isn't it? 1, 3. No, wait, this is... I'm not sure what I'm looking at now. AP Physics 1, AP Stats, AP Pre-Calc, is any civic math I should do over the summer to sharpen for next school year? AP Stats is a lot of memorization, is the unfortunate truth. So I would just get a jump start on the pre-calc, to be honest, because the pre-calc will help you with physics also. It's the fact that each L... Oh, you're writing n squared, right, as the sum of odd numbers. Huh. Yeah, I guess, Felix, my question is, why is that... I would expect the first difference to be the number of dots that are adding to each layer. So there's something about this picture that I'm still not quite sure how to interpret. It is a neat picture, though. I don't want to keep K-pars waiting for longer than I already have. Okay, so K-Vars, if you're still here, what do you want to start with? I'm happy to start with anything. We've talked about a few things now. Whole square is x squared. Strips are 2x plus 1. Oh, okay. Interesting. The strips are the first difference. What if your whole life spirals and you become a math major? Let's hope it doesn't come to that. That'd be very dark. You worked out the regression thing in class before. You just want to see how you would approach it. Okay, well, let me. I mean, if you, I'm happy to start with that. If you want to steer me in a different direction, though, please steer me. So this is what you wrote in chat earlier. I need to grab my notebook for this. What section of my notebook did I write my notes in for this class? Here we go. Wavelets. Linear algebra. BCA. Okay, supervised learning. This is what we want. What's up, Sword? Okay, found the regularization section. Yeah, I'm not sure if I'll be able to even do this, but I'd like to at least understand the question first. Or it's like understand really what the question is saying. Then we can try to talk about it. The constant, you need to basically try different values for that constant and see what comes out. The constant controls how local you are. It's not like it makes your Gaussian wider or narrower. A wider Gaussian is less local, a narrower Gaussian is more local. And there's going to be some sigma that gives you the least error. And that's how you would choose sigma. I'm looking for a lambda. Here we go. Okay. Yeah, that's going to be called like a hyperparameter sword, I think. Okay, that's what I've written in my notes. That's the, I think, the relevant thing here. Sword. A large standard deviation is a wide Gaussian. Yes. A larger constant is less local, so you care more about farther away. An example of when it becomes two-way mathematically. Roxra? Oh, okay, cool. You would just do this with generic A's, B's, and C's. Yeah, exactly. She prefers getting the dimension to work out. OLS estimator. Oh yeah, square, what's your fortune? Your self-confidence is warranted. Ooh, that's a good fortune. Okay, let's write down what Gaypard says too. OLS estimator B. This is just your good old linear algebra least squares regression. We all know and love. Ridge reduces the lambda to regularize. Yeah, this looks familiar. I bet I had this written down in my notebook somewhere. I think prime is transpose here. Yeah, I see it written down in my notebook right here. Okay. Okay. Nice. We're on the same page. um, if you pick two different x, and if you go same distance away from both x, show the same level of careness. Yeah. I think I mean, you don't, I guess you don't have to, but the simplest thing will be to choose the same constant for everything. You don't, I guess there's no reason you have to do that though. Okay, so to answer Fenlox's question, this is a problem in supervised machine learning. But in typical machine learning fashion, it's really just stealing classical math problems and renaming them. So this is an evolution of it, but imagine normal linear regression and normal linear regression. You can do a linear algebra thing. With a least squares problem. Sounds good, Sword. Sleep well. And I believe that's what this formula is. It's the linear algebra solution for like least squares. Like, why is your data that you're training with and is X the real data? Or whatever your test data is? I'm a little rusty on this. The matrix of predictors. Right. Okay, yeah. Oh god. I'm thinking back into my memory for this. And so in normal least squares, you're minimizing you minimize basically this thing here. where f is some linear function and y is your actual data. In the linear algebra thing, you can get a matrix equation for what the coefficients of your line should be. AC is amazing, Lucas. I wish I had it. The thing that machine learning sprinkles on is something called regularization. A line is just a fixed thing, so you don't worry about it for linear regression. But if you think of like a Fourier series, those like a line is one finite thing, but a Fourier series goes off to infinity. And you don't want to use infinitely many terms in your model. You want to penalize the model the more terms it uses. So we favor simple models over complicated models. So I'd rather have a Fourier series that's decent that only uses, say, 4 sines and cosines, rather than a Fourier series that's perfect on paper but not really perfect that uses 100. It's also called overfitting your data. There's a little more to it than just overfitting. There's like a subtlety here that I don't quite remember. Yeah, basically, when you go from linear regression to other types of regression, you tend to need to penalize complicated models, or else you get a really bad model. That it does minimize the error, but not in a productive way. What are the application benefits of knowing differences or pi? I mean, there's no real benefit to like memorizing pi, if that's what you mean. The application of knowing the differences is that you're learning a numerical method. Oh, eats into white pi like Zach. You basically have sneakily learned a way to approximate derivatives, which is really helpful in differential in like applied differential equations. Are we looking at the leaderboard, Lucas? That's over a long time. I've known hard luck for years, but I guess so. Okay. Sorry, K-Parts. I keep getting distracted. How do I want to do this? The limit definition of a derivative is this. Instead of h being really small, though, and going to 0, I'm just going to say h equals 1. And so this is like the basis for approximating derivatives with h. And the smaller h you use, the better approximation you get. So this is discrete, this is continuous. But this is the first difference that we were talking about earlier. Sounds good, Lucas. Sleep well. Okay. Yeah, look up like Euler method, I think it's called, for differential equations. It's basically the jumping off point. Okay, back to K-bars. Some data have many predictors in few cases, like in genomics, data with billions of SMPs, hundreds of observations. Typical regression fails because it is a non-square. So this is IN rather than IP. It's in a side a bit. Okay. I basically asked to show var b ridge. It's not how you spell ridge. given x is less than var b ols given x. I might have written that. I wonder if that given x was including the subscript. Writing this as default regression, ridge regression is regularized regression, tames variance, introducing some bias. Yes. Okay. Ridge and lasso and their hybrid elastic net are used for predictor selection. Right. Okay. Thank you, K-Pars. EB ridge given x is not equal to BOLS. Okay. Okay, and how do I need to remember how we measure the variance of this? That's step one. I really want to learn more about machine learning. But that there's some kind of like sneaky functional analysis type of stuff that was lurking in the background that I kind of, and also a lot of probability that I don't have a good enough understanding of to properly learn the background for machine learning. How many numbers are there? Aleph. You know, like there might be Aleph 0. It's the size of the set of real numbers. Oh yeah, it's Aleph 0. I called you Aleph, I guess. Oh wait, no. Aleph 1 is real numbers, maybe. Aleph 0 is natural numbers. Yeah, sorry. Yeah, that basically Cantor's thing is what kicked this off, and then people like generalized it to allow bigger Alephs. So you can make sets that are even bigger than the set of real numbers, I guess, if you care to. Change, thank you so much for the raid. I hope your stream was good. Brenner's new here. I play games too, but I'm also a math streamer, and you just walked in on me working on a problem involving machine learning that K-Pars gave. And I'm currently looking back through my notebook to remember how the heck you find the variance for the error of a machine learning model. Change, I hope your stream was good. Thank you again for the raid. Variance of the estimator. Math Z. Like, I surely have this written down somewhere. I just can't remember where. Mean like this. E of x minus mean squared. Yeah, right. I just... Okay, wait. I do have... I don't know if this is the thing that we want. If you do enough work on this, you can get the bias squared plus variance plus noise. Because I have a whole bunch of steps between these two things, but I assume we want something like what I just wrote. You look over your attachments, become enlightened. That's true. It's very zen. Except for my attachment to the Leo Lectures YouTube channel. True. Oh yeah, Change. I noticed you hadn't streamed in a long time, but I'm glad that you're back at it. Yeah, and feel free to go and take care of yourself. When it's hot at 2 a.m., that's never fun. This is annoying. I don't remember like why it. I don't remember what this expectation actually it really is. I'm too rusty on this. It's the expected value of the error. Why can the x's come outside though? In your notes, Kpars. Usually hot at 2 a.m., but not temperature wise. Sounds good, Change. Glad you like it. not a function of y, you can take it out of the expected value. Oh, that's because the expected value is linear. Right. And y is the only thing that's like changing and the x's are basically constants. And so then for some reason the expected value of y given x is x times beta. What would beta be here? CLS predictor. Okay. Hey, Papadoria. Depth to be linear. I think for this it is supposed to be linear. Maybe. I don't know. You understand beta just alpha? What's happening in the second bit? Oh, that's for expected value. And so you use that to find the variance. Okay. Oh, okay. That makes more sense why we get the predictor. Okay, I thought we were already on the variance. That's why I was confused why we get the predictor. Okay. Yeah, it gets really complicated with like the hats versus not hats. Not even railway cars either. Damn, that's hard, Leo. Okay, so then we use that for the variance down here. Wait, do we? Is using properties of variance directly. Okay. Right, that's the predictor again. For ridge regression, it looks like that. Hmm. Yeah, I. It sounds like Leo should have a better idea what to do than me. I'm just I'm struggling. I'm too rusty on this. Jensen's inequality. I've heard of this before. Jensen Wang. Oh, that's the NVIDIA CEO thing. Oh, wait. Okay. Yeah, I see now. Pretty sure Jenny H also came up with this. Hmm. Yeah, I'm sorry, Capers. I don't think I have anything smart to say about this. I'm too rusty. This is the part of machine learning I was kind of the worst at. I think it's really cool, and I'd like to be better at it. Yeah, sorry. I really would like to understand how to do this problem. It would take a lot more thinking than I can really do on stream, though. Yeah, probability plus linear algebra. That it equals machine learning. That's the equation that we're using here. Okay, there was another thing about machine learning you were talking about, K-pars. Do you want to talk about that too, or like how are you feeling? Pursue math in your free time this summer? Hell yeah, Roxra. A weird math logic puzzle. I'm probably gonna wrap things up soon. Oh yeah, the integrated thing. Yeah, yeah. Like I can bring up your chat history to see it. Um. Oh yeah, that wasn't like that wasn't the same as like a thing. Yeah, Hodor, we can at least like look at your puzzle though. I don't know. I'm kind of running out of brain power to solve it, or to solve much of anything right now. Same with you, Leo. We can at least like look at it and think about it for a bit. Okay, that's what Kapar said earlier. How do you even start? Uh, if I would, um, Where is it? No, what? I'm fucking it up. Because I'm getting tired. That's the thing I mean to click on. Roxer, I will just choose something off MIT OpenCourseWare and follow it. Anything you're interested in math. I guess they don't do pre-calc if you were interested in that. But the like, I guess it'll be a little more advanced than like high school math, but it'll provide you a structured thing that you can follow along with. Yeah, for pre-calc, Khan Academy or OpenStax provides textbooks if you prefer to like read instead of following lectures. Pre-calc. It's free, it's legal. Well, yeah, I not everyone is a fan of illegally obtaining textbooks, so okay, so back to what Kpars asked. Time series modeling, if you're going to call difference models integrated, why? ARIMA stands for autoregressive integrated moving. I mean, let's just try Googling it. I don't know this offhand, but maybe Stack Exchange is better. Differentiating a series that is not integrated is certainly problematic from a statistical perspective. Oh yeah, it's like, you know, that this PDF fell off the back of a truck, and you don't need to ask more questions than that. Oh god. Hey, but this is what Roxer was doing, a way more complicated version of it. This is the first difference, though. Difference the series to make the series stationary constant, then in forecasting it just runs the other way. I see, okay. Yeah, me too, Palvadoria. It's a great day when that happens. Uh, I don't think I can answer that question about why they would call it integrated. If this is like a discrete derivative, maybe we're reversing that to get the original thing back out. But um, you think that's it? Okay. I'm getting too tired to want to read all these symbols. This is too many psis, or is that, yeah, psi. There should be a limit to the number of psis you can put in a comment. Um, yeah, sorry, I'm kind of phoning it in because I'm getting mentally tired now, but I don't want to like leave people hanging either. Which I guess that means that I'm half-assing uh the stream, but that's just what I do, I guess. Okay, so I think so Leo posted a question too, and Femvox I think already solved it, but let's read the question. sea of size. I appreciate you understanding K-parts. I really like the stuff that you're asking about. I think it's super interesting. It's just, it's not easy in the first place, and I'm rusty on it. Two integers a, b, which can be expressed as sum of squares. Too many sides. POV my parents when I'm telling about my life. So, funny enough, I just learned about the first part of this question as part of PDEs. It's actually it comes up in the study of Chladni plates. And basically the eigenfunctions for the Laplacian, the ones that have like multiplicity, the degenerate eigenvalues, correspond to interesting patterns in Chladni plates. And you can tell if an eigenvalue is multiplicity if it can be written as the sum of two squares. The last quiz question. Yeah, if I had more energy, I could write it out better. But it is like a neat little way where number theory comes into PDs. Secret the basis of Erdős's construction of the unit distance problem. Oh, this is the product. Okay, at the sum of two squares. We're comparing these two things and looking for connections. I wrote them in reverse order, I guess. I mean, to me, this just straight up looks like a number theory question. Oh. A squared plus b squared is a plus ib times a minus ib. So we take this equation and multiply it by like the conjugates each side to get what we want. To be honest, I still don't. Honestly, I'm not even completely following this solution. That just seems like a natural thing to do, though. How many weeks do you estimate it would take to get through pre-calc? It is extremely subjective, as you say. If you're dedicated, and I would not recommend burning yourself out, but if you do, like, do it to the point where you're burning yourself out, like, okay, for 1 to 2 hours a day, 8 weeks would be kind of quick, but maybe doable. Like 12 would be better. Took me 10 years, it did. But like what I would do, Roxra, is like choose a textbook or some resource that has a table of contents. Figure out what you want to cover. I don't know why I'm talking like this. um it's really annoying. And no, so choose a like Khan Academy or a textbook. Look at table of contents, figure out what you want to cover, and kind of adjust from there. Like budget a certain amount of time for each chapter. Somebody did a whole chapter on Gaussian integers of working out when they were prime. Okay, nice. Oh wait, or you mean like maybe for planning you mean to knock it all? I was interpreting that at first as like knocking out all of your studying in one day. Yeah, just study for 24 hours straight. Okay. You did mean that. You know what? I believe in you, Roxra. You can do it. Zi has a whole world of primality. Essentially, lots of these problems, like when can you write down numbers a squared plus 3b squared, turns into a factoring problem on some other ring of integers. Okay. Needed to find numbers m that are expressed as the sum of two squares many different ways. Yeah, it's the exact same thing with Chladni plates. Yeah, it would be my worst nightmare. I feel like I should just suck it up and learn more about it, because maybe I just need to get deeper into it. And I'll start to like it, but like, it's hard. Take a product of n numbers, each express the sum of two squares. Okay. Feel about real analysis? No, I appreciate real analysis because applied math is basically just taking pure math and using it to find tricks to accomplish real world tasks. And real analysis is like the most directly applicable thing. So like numerical methods to solve differential equations are kind of based on real analysis. Introductory real analysis is like drinking sand. Yeah, I agree for introductory real analysis. I missed me with epsilon delta proofs. I still don't understand those. But once it becomes like once they stop testing you on epsilon delta, I like it more. Another exercise for you guys using Gaussian integers. Also primes congruent to 1 mod 4 expressible sum of two squares. Why though? Oh, I think I've heard that. I don't know if I want to solve it, but Mega, sure. I want to wrap things up soon, but I'll at least look at it. At this point in the stream, I'm pretty like mentally tired, so I don't know if I'll have anything smart to say, but maybe someone in chat will. And Papadore, if you want to share your logic puzzle too, the same offer goes to you, where I probably won't be able to solve it. We can at least look at it and talk about it. Yeah, so like that's my goal when someone asks me a question. Like if I can't solve it, at least contribute to it in some way. But I'm getting to the point where I can't even do that. Oh, the proofs where you have to show n different statements are all equivalent. How many ways are there to do that? Well, I guess you would go pairwise. Well, would you? So, how many minimal strongly connected directed graphs with n vertices are there? Minimum is if you remove an edge, it's no longer strongly connected. Is strongly connected. I need to look that up. Every vertex is reachable from every other vertex. Okay. For a direct graph, that's more subtle than just being connected. Okay. Oh yeah, fair enough, Leo. Composites and basic trig stuff. What I remember learning in pre-calc, AP pre-calc might be different. But I remember like the first half of it was all trig stuff, and unit circle. The second half was all like kind of more advanced functions, like higher degree polynomials, probably stuff about logarithms and stuff. Maybe you're just ahead of the game, Mercs, or I don't know, like look up the College Board, what they say AP pre-calc covers, and maybe match it up with whatever Khan Academy calls it. Maybe Khan Academy just has a different idea of pre-calc. And then Leo Lecture's asking Megalomorph if the nodes are labeled or if just up to isomorphism. I assume it's labeled though. If for two vertices there's only one. Labeled, yes. Okay. Um. Okay, just get everything in one spot. Let's look at the example. So for 3, you can have 2 different cycles. 1, 2, 3. You could have 1 to 2, 2 to 3, 3 to 1, or it's reverse. And you can have 3 things that look like lines. I like those odds. Wait, 3 things that look like lines. Oh. Yeah, maybe I shouldn't have drawn it in a triangle. We need 5 different things. Oh, okay. Wait, this is the. I don't understand what the line one is supposed to be. Yeah. Leo's thinking of recurrence relations. AN is equal to n minus 1 AN minus 1 plus n minus 1 factorial. Induction is probably, or like recurrence is probably a good idea. So then n cycle or an if and only if connected to an n minus 1 minimal. Hmm. So you're saying you build the n minimal one out of the n minus 1 minimal one, but that we might be missing other types of graphs that can't be constructed like that. Yeah, I manually copied it. Okay, so these are the two triangles with the directions reversed. Oh, okay, this is the line idea. I didn't realize that we could use 4 edges. Okay, that makes sense why there should be 5 cases. So, I mean, but I guess, are these not minimal then, the 3 cases on the bottom? Well, I guess it's still, okay, no. It still meets the definition of minimal, because if you delete 1, it's not strongly connected. That's the point. Okay, that makes sense. Hmm. Hmm. Yeah, I mean, that, I guess what Leo put could still be a good basis to work from. We just need to account for whatever is missing. Maybe I shouldn't have erased what Leo wrote. Starting from complete directed graph. See how many edges you can remove. Oh, maybe. So you can have more branched off of one. It's missing a lot of cases? Okay. A lot of times OES provides references, but... Huh. Well, what about this? Oh. The Google AI knows about it, apparently. Osmania University? Thesis. Come on. Oh, do you have to get them in person? Wow. I assume that would be the thing that will be publicly posted. It's a video, though. That's not the same person, though. Hmm. Seems like it was a thesis of some guy who now works at DocuSign. Live in the library at the University of Osmania? Oh, yeah? How frustrating this isn't a publicly available reference. Like, how did this person get a hold of it? This, I mean, what about this? Oh, that's just a search history thing. Okay. Well, fuck it. Uh, I don't know. Your name is something like Jovovic. You just summon any work on combinatorics? I guess so. Yeah, I mean, Ian Stuckey has been doing like a bunch of graph theory stuff recently. I don't know if you've already tried asking this question to them. Um, you did? Okay. Yeah, that's a cool question. I was use a math professor. Oh, that's so annoying about the thesis being like I I thought it was a thing that schools just like made public, but I guess not every school. Um, yeah, I'm sorry. I don't think I have anything that I can contribute to this. I do think I want to wrap things up too for the day. I might try to see if there's a way to dig up that thesis. I might keep trying on that, but for actually like just slotting this straight up, I don't think I'm going to be of any help, unfortunately. Yeah, thank you for trying. Even if I can't help, there's always a chance that someone in chat could. The recurrence process I have for it is a messy partition-like thing I don't think is very useful. Yeah, I mean, a messy answer is better than whatever answer I could get. Um, Leo, if you come up with something good, if you're in my Discord server, feel free to post it there, and I can make sure that Mega sees it. Um, but yeah, I think I want to go and eat some food now. I haven't Mega saying you couldn't come up with a occurrence at all, so start with a node, add a cycle around that node. Then you can add a cycle around any of those next nodes until you hit n. So like, if you wanted to go to the fourth one, you could add a fourth node here with a cycle like that, is where you're starting at least. And you could do this with any of the three nodes here. But yeah, okay, I can see where you then need to include all the other things. Because like, or as you get into more nodes, like you have other shapes like this you need to worry about too. Avoiding double counting, also not missing anything, and also maintaining minimality is tricky. Yeah. Add a cycle on one, then cycle off one. Hmm. It's like counting arrangements of carbon atoms in organic compounds. That'd be a crazy connection. I just googled that phrase to see what would come up, but nothing that relevant is coming up. about counting the number of carbon molecules. My generation algorithm gets everything and is minimal, but it does double count. Okay. To add all your cycles off of one at the same time, treat as a set. I think because multi-indexed. Oh god. Okay, I really do want to get some food now. I'm sorry to cut you off, Leo, if you're still typing out more thoughts. But please do, like, let me know if you come up with something and I can just, like, pass it along. Get you something? Something yummy? Okay, I'll be right there. Yeah, I'm gonna cut the YouTube stream off here, so Leo and I knows who's lurking, thanks for being here. On Twitch, we'll look for a raid. So yeah, have a good night, YouTube. Oh yeah, I look forward to you finding that thesis, Leo. Good luck.